it time for Planet B? That is the question. Let me welcome you to Leeds. You join us here at Leeds City College Quarry Hill today, and I hope you will be able to make yourself comfortable in whatever place you're following us online. My name is Martin Dominic, and I'm the president of the Network of Researchers on the Chemical Emergence of Life, NoRCEL, as well as co-director of the Center for Exoplanet Science at the University of St. Andrews. NoRCEL aims at fostering a global inspiration community of original creative thinkers, cutting across disciplinary confines, who are keen to engage in respectful discourse in order to explore new directions and to build collective endeavors. Today's event is part of our Blue Earth Project initiative, with which we're building a bridge between the urgent sustainability of life, the co-evolution of life with its environment, and humankind's responsibility for the ecosystem of our small planet. This event has been designed and set up together with Sohan Jeter, founder and chairman of NoRCEL, Rees, CEO of NoRCEL, Oleg Kotsiubenkyo, vice president of NoRCEL, Miriam Palacios Perez, leader of the NoRCEL Latin America Hub, David Smith, who is doing microbiomes within NoRCEL, and Katie McGrath, who is our NoRCEL chief administrator. We've invited 6 panelists to give us their thoughts on Is It Time for Planet B, which will lead into a discussion about human exploration and responsibility. They have been deliberately chosen with the expectation that it would address the topic from different perspectives. We did not tell them in which direction they should develop the question, and I hope that you're as curious as I am to find out where they will be taking it. Each panelist will deliver an opening statement, and we'll have those before breaking for lunch, after which we'll enter a debate starting at 2:15 UTC, which you all can actively participate in. Stephen Hawking proposed a doomsday scenario in which humanity might have as little as 100 years before leaving Earth. Elon Musk does not wait for that long. Humanity successfully conquered planet Earth and entered the space age with the launch of Sputnik 1 in 1957. Is human settlement beyond our whole planet a natural consequence of our existence and of our capabilities for exploring our surroundings? Or do we fall for false narrative? Where lies the future of humanity? And what are our responsibilities with respect to an environment that we all critically depend on? You shall see me later, and I'll now hand you over to Sohan.
Since this is international forum, I welcome you all, and good morning, good afternoon, good evening, and if just after sleep, just as we're getting started, good night. And welcome all of you. As I said, my name is Sohan Jeter. I'm the founder and chairman of NoRCEL, Network of Researchers on the Chemical Emergence of Life. And this was set up in 2013, last year. Well, it wasn't actually last year, it was a year before we started talking about what to do about the planet Earth. And we came up with a plan, this type of format. It's very, very special format, but I'm not going to go through because I've got a lot of going through. But what you can do, write to me, I'll give you further input in relation to the Blue Earth Project, how we came to be in this type of format. It's kind of, we call it double blind in this format, in the sense that actually audience doesn't know what we're all about or what the talks are going to be about. Neither do the panelists, and we don't call them speakers, the panelists, because they'll be leading the discussion. They don't know what each and every one of them are going to talk about, so it makes it double blind. So it's something you'd be expecting, the unexpected. And so let me move on to the next slide. I want to get through 3 bullet points, more or less. This is the team, NoRCEL team, and obviously Blue Earth Project is an innovative initiative of NoRCEL. I've only 3 messages actually, and which is, what is Blue Earth Project? What is the mission statement of Dept? My friend Chris asked me that question last night. I hope I'll be able to clarify that. And how can we achieve this new order? And as I said, Dept was inaugurated in 2022 last year, but the discussion started a year before that. And Dept is a totally voluntary and receives no funding, outside external funding at all. By the way, I'm dyslexic, so every now and again I'm going to be hesitating and read something completely different when what's not even there. So Dept is totally independent, no affiliation with anyone else, and Dept aspires to appeal to those with a similar aspiration. And this is why you hear in forum here at the Quarry Hill campus, Leeds City College. And we also have a lot of people logged on internationally. And Dept promotes protecting the Earth, the biospheres, and the ecosystem. Message number 2 is that to highlight issues affecting Earth's biospheres and the ecosystems, and to promote sustainability, to disseminate reasoned scientific discussions and arguments. And of course, the third message is to understand that every living entity has a right to be here alongside us on this planet Earth. And what are we doing? We're slaughtering them as time goes by. Second is to pose difficult questions and expect the unexpected. And then to debunk fake news and pseudo facts. Encourage collaborative and collective interaction. This means we would like you to get involved with Dept. We will have a website very soon, and you'll be informed of it, and we will actually take put everything on it, and you can actually interact more or less in real time. And so, still on the message 3, so last year we actually considered, is humanity settling its own fate on ecological survival? And the answer is answered in that paper that we published last year. And of course, in 23, we are in a time for Planet B, which our president outlined, Martin Dominic, prior to me. And then next year is human madness. 2024 will be human madness. And Dept's take-home message, what is it? Well, Blue Earth Project is concerned with the feasibility of maintaining Earth's biosphere and ecosystems by focusing on reasoned logical debates and thus promoting sustainability. We can't get enough to repeat this word sustainability. It's a motive word, and I should think that we should heed to it. Thank you very much, and for listening to me. Thank you.
Okay, so I'm Elias Hadjitheodoridis, the CEO of NoRCEL, and I'm happy to invite you to this event. and I will introduce the panelists that are here with us. And one of the panelists is Erika Nesvold from JustSpace Alliance in USA. She's an astrophysicist, co-founder of the Space Ethics non-profit JustSpace Alliance, and author of the upcoming book of Earth, Ethical Questions and Quandaries for Living in Outer Space. Then comes Anders Sandberg, Future of Humanity Institute at University of Oxford. He's a senior research fellow, researching existential risks, emerging technology, reasoning under uncertainty in humanity's long-term prospects in the universe. And then the third panelist is Chris Thomas, Levenshulme Center of Anthropology and Biodiversity, University of York. And he's an ecologist and evolutionary biologist who studies the positive as well as negative responses of biodiversity to humanity, and who would like to work out how we can survive on planet A. I welcome the panelists. Please come to the floor.
Hello, as I was just introduced, I'm Erika Nesvold. I'm an astrophysicist by training, but over the past several years, I've gotten very interested in the ethical and human rights challenges of space settlement. As you mentioned, I have a book coming up on the topic. So I'm especially intrigued by questions like the ones that we've been posed at this event. Is it time for Planet B? The term Planet B, as most of you probably know, is usually used as a play on words based on Plan B, which is the backup plan that you switch to in a heist movie, perhaps, once Plan A has gone terribly wrong and you have to abandon it. So the idea of a Planet B, especially when the term is used by environmental activists or on a t-shirt, usually means the backup planet that some or all of us could go to instead of Earth in case something goes wrong with our home planet and we have to abandon it. Earth certainly feels very precarious these days, so space colonization advocates often invoke eggs in baskets and argue that we need a backup planet B now more than ever. There's plenty of debate over the technological and biological feasibility of creating a self-supporting branch of human civilization on a backup planet B. There's a lot of obstacles, though, to long-term survival in space for humans and our biosphere. There's the radiation, the lack of breathable air, drinkable water, the temperature extremes, the vacuum, the low gravity, the lung damaging dust. We don't know yet whether we can grow crops or gestate children in space. There are a lot of very smart people working to address these challenges and to identify other potential barriers to living in space. But I'd like to argue that there's one particular source of potential harm in a hypothetical space settlement that we should be spending more of our efforts figuring out how to mitigate, because this is a threat that's present and causing significant damage here on Earth today. What's this great threat to the safety and stability of a space settlement? Well, it's that humans will be living there. There's a rich variety of potential apocalypses and existential threats that people will cite when they argue for a planet. There's nuclear war, impact by an asteroid or a comet, a devastating pandemic, climate change that leads to ecological and civilizational collapse, a sterilizing gamma ray burst, the murderous artificial intelligence, and eventually, inevitably, the evolution of our sun into a red giant that engulfs the Earth. But note that most of the items on that list I just read off would be caused intentionally or unintentionally by humans. Not all, some of them are natural phenomena, but most require the presence of humans somehow. I mean, we all know that we're consciously, knowingly causing harm to the stability of our biosphere on Earth right now. So my question is, what's stopping us from bringing these same threats with us to a planet B? Will our descendants be sitting on a panel like this one a few hundred years from now, wondering whether we need a planet C? Now, some people have argued that we shouldn't attempt to settle space at all until we demonstrate that we're mature enough as a species and a society. This includes my colleague Linda Billings, who argues that, quote, if and when human beings are further evolved culturally, intellectually, spiritually, and all these important aspects of being human, then perhaps we could proceed to settle space. That's not the argument that I'm trying to make here, nor am I saying that humans as a species are some kind of inevitable planet killers, that it's in our nature to leave destruction in our wake wherever we go. I find that arguments about human nature often inadvertently and incorrectly extrapolate the characteristics of certain human cultures to the species as a whole. No, what I'm saying here is that part of figuring out how we would shape another planet's environment to make it habitable for humans is figuring out how to shape our own laws, economic priorities, values, and worldviews to make our civilization capable of living sustainably with our environment, whatever planet we're on. To do this, we need to advance in at least 3 non-technological categories. We need to improve our relationship with each other, with our environment, and with future generations. Let me just go through these one at a time. So when I say we need to improve our relationship with each other, I don't just mean that we should achieve world peace so we can avoid nuclear extinction, although of course I'm in favor of that. Attempting to live in outer space is not just dangerous, it's precarious. There's no buffer, no margin of error. On Earth, if society fails you or rejects you, you can at the very least expect to keep breathing while you figure out what to do next. Depending on where you live, you probably have at least until the sun goes down to protect yourself from dying of exposure. And you can probably find enough water to avoid dying of thirst, although there's no guarantee that it'll be clean. But you can survive on Earth for somewhere between hours to years, completely on your own, with no help from other humans. In space, this environmental safety net does not exist. If you're kicked out of the habitat, you're dead in seconds. So we'll need to improve our social safety net. Not only because the idea of moving people out of an airlock to try to survive on their own on the surface of Mars is pretty dystopian, but because the people living in a space settlement will depend on each other for survival, on their community more than they ever have on Earth. So we'll need to step up our game in terms of cooperation if we want a planet B to be feasible. I also mentioned that we need to improve our relationship with our environment. This is a point that's taken on particular urgency here on Earth. And I'm really glad to see, especially recently, that people working in space science and the space industry are starting to really think about ways to protect the space environment from ourselves as we expand our activities beyond our planet. Living on a planet B would mean irrevocably altering the environment for our own Earth. That's the nature of life, it alters its environment. But our motives for finding or creating a backup planet will determine how we treat that environment. Are we just going to fill our pockets up with whatever resources we can extract, dump our toxic waste, and build enough ships to get to a planet C, just valuing growth above all else and using what William K. Hartman calls a disposable planet mentality? Or should we take the time to learn how to live as part of a larger system, giving and taking from our environment in balance and expanding to new worlds only as a deliberate, considered choice? This is a decision we'll have to make in the coming generations. Do we want to move across the universe like some kind of invasive plant, just leaving barren, scarred landscapes behind us? Or do we want to be gardeners, tending to the health of every thought we start, as well as the one we started with on Earth? Just note that this last model that I quite like of humanity as a gardener in space is from Robert French's masterpiece. This question ties into my last point, which is that if we want to ensure the long-term survival of our species on planet B, we need to improve our relationship with future generations. Now, this might sound a bit tautological. Surely, if we're discussing how to avoid an existential threat, that must mean we care about future generations. But I argue that we have to do more than just toss an extra planet at those future generations and say, there, we've doubled your odds of long-term survival. Goodbye. How much of a planet's non-renewable resources should we set aside? What kind of infrastructure can we build with a portion of those resources that will benefit our descendants as well as ourselves? What values can we build into our legal, political, and economic systems to enable future generations to avoid repeating our mistakes? Once again, the work we do to answer these questions will also help us improve our odds of avoiding existential threats on Earth as well as in space. So I've argued that building a sustainable civilization on any planet, including this one, requires that we improve our relationships with each other, our environment, and future generations. So how do we do this? The first step, of course, as always, is to recognize the problem. And in particular, I often write that anyone developing plans for expanding human civilization into space must identify the social weaknesses and challenges of those plans, as well as their technological. Next, we need to engage with experts. There's no need to invent the wheel here, by which I mean there's no need for a bunch of astrophysicists and engineers to try to invent sociology, anthropology, political science from scratch. I appreciate that there's a social scientist on the panel, Kathryn. You'll see her talk later. But on the other hand, there's only one social scientist on the panel. Let's see if we can get those numbers up. Let's engage with experts like Kathryn, who have been thinking about space from an anthropological perspective, or people who might not yet have considered their work in the context of space, but who have the expertise to help us learn what's worked well and what hasn't here on Earth, so we can apply those lessons to the next planet. What can environmental justice experts teach us about balancing the needs of everyone in a population, plus future generations? What can we learn from economists developing circular, sustainable economic models that help us navigate between societal needs and ecological constraints? We also need to partner with communities that have demonstrated expertise in things like sustainable agriculture or multi-generational planning. Western science is finally getting around to noticing that the sustainable practices and worldviews that indigenous communities have been using for generations. But notice that I said we need to partner with these groups. I don't mean that we should just swoop in, grab whatever technologies and methods look useful, and then rush off to space with them. If space is going to be a human endeavor, let's make it a collaborative one. And finally, throughout all of this work, we should aim our research and planning to benefit the current and future populations of Earth, as well as any other place we end up living. That way, if it turns out that it's actually physically impossible to sustain a permanent human population away from Earth, at least we haven't all been wasting our time. So, is it time for Planet B? We do not currently have the ability on a technological or a societal level to build a replacement for Earth. But more importantly, this shouldn't be our model as we work to develop those abilities. This is a good time to start talking about our vision for a Planet 2, a sequel to Earth, not a replacement. We can ask things like, how would the inhabitants of Planet 2 grow their food, recycle their water, and build their habitats, which can help us develop new technologies. But we also need to ask, how will they live with each other and their environment? And most importantly, we need to think about what we can learn from these conversations, like the ones we have today, that can help living humans on Earth right now. Thank you for your time, and thank you to the organizers of this event. I really look forward to the panel discussion.
Okay, I'm going to try to be the philosopher in the armchair here, although it's a virtual armchair. So, where is Planet B? I would argue that we're on Planet B right now, or rather inside it. We're in an artificial environment that provides us with a nice heated environment. We're getting light, we're getting air filtering. We're getting a lot of important services for keeping us happy here. And behind the scenes, of course, there is a vast global infrastructure of supply chains that provide the food, the energy, the information that is needed to sustain this. I would argue this is also a very extreme life support system, and it's actually necessary. So to paraphrase David Deutsch, without technology, humans can't survive in Yorkshire. He was talking about his native Oxfordshire, but I think it's true even here, that without clothing, without tools, we wouldn't last very long at all, even in the fairly pleasant countryside here on Earth, with a very breathable atmosphere, with water that is actually liquid, etc., etc. In order to survive, we humans need to make tools. We need to coordinate to build traps. We need to actually change the environment. It's just that we have scaled up this process tremendously over the past millennia, and even more over the past few centuries and decades. So we are in a sense living on Planet B, and by that I would mean the human technosphere. Now, in this talk I'm going to mostly be calling the technosphere Planet B. Occasionally I might be referring to other Planet Bs and Cs and Ds up there. Now the technosphere is an interesting object. There have been some estimations that it weighs about 30 trillion tons. Most of that is concrete, which is a really fascinating thing. It's a form of carbonate conglomerate rock that we make. You can get somewhat similar chemical compositions naturally here and there, but it's rare. But we humans are, of course, putting it everywhere. We're also a major erosive force of rock. Much of the rock that is broken down today is broken down by humans using explosives, quite often to make place for stuff made out of concrete. We also have this environment where, using the Haber-Bosch process, we're responsible for about half of the nitrogen fixation on the planet. Life on Earth has been spending literally billions of years of figuring out ways of getting nitrogen from the atmosphere into biological useful forms. About a century ago, we humans figured it out. And indeed, most of the nitrogen in our bodies in this room is fixated, not because of natural fixation by a bacteria in the ground, but because of a high temperature chemical reaction. And this keeps a lot of people very happy and healthy. The downside is, of course, that we're also messing up the climate. The downside is that we're taking a very large amount of the net productivity of the planet and using it for our own purposes, quite often to a very serious detriment for the rest of the biosphere. We're also creating a lot of strange diversity. So exactly how many species of living beings there are on Earth is very debated. I think the current estimates are somewhere in the ballpark of 10 million. On the other hand, I think it's 35 million different species of things you can buy on the Amazon marketplace. Now, maybe equating them to snow globes and pieces of furniture and books with insects, with palm trees, with nitrogen fixating bacteria feels a bit unfair. But it's very clear that the technosphere is a rather strange object. And it's not a simple object. Part of that is, of course, because it contains a lot of information courtesy of our own somewhat limited brains. We are symbiotic with this technological system. We use it to survive and thrive, except that we didn't know much about ecology until recently. So we didn't quite get how bad things could get if we did it. We are embedded in it. It used to be that we had this idea that we're embedded in nature, which is totally dominating us and we're totally dependent on. And that largely remains true. If we don't get much oxygen production from the plants, we're not going to survive that long. Except that actually it takes a fairly long time for oxygen to disappear from the atmosphere. So if we noted that plants stopped making oxygen, we would actually have a surprisingly long time to figure out solutions. And I think we would, because we would be highly motivated. The interesting thing here, however, is that we have this very dynamical system. The technosphere has not always existed, and it's not always going to exist in this form. And that gives us hope for actually making Planet B compatible with Planet A. So instead of going to the Planet B in space, we are in some sense building it here on Earth. Now, that means that we might not necessarily have to terraform Mars, which would be an interesting and slow and expensive endeavor that might not necessarily be important. But I think in particular, the space settlement people's work on making self-contained and self-sufficient habitats are really interesting. And this ties into a long history of ideas that links actually the biosphere and the technosphere quite strongly. So if we go back in time, the concept of the biosphere was popularized by Vladimir or Volodymyr Vernadsky. He was a Russian-Ukrainian crystallographer, geologist, but also early biologist, who popularized the idea that we have a geosphere and a biosphere. These are concepts got from Edward Seuss, who did it a bit earlier, but also a noosphere, the world of intellect, the world of communication, and what I would call the technosphere. So he pointed out that the biosphere is shaping the geosphere to a large degree. This was a rather radical idea in the 1920s. It took a long while before this actually became common recognition. But then he pointed out that the noosphere is going to be affecting the biosphere more and more. And he was also pointing out that this is about systems. There are the flows of matter and energy and information. And this is quite important for understanding what's going on. Now, this systems thinking shows up in various forms. So one branch moved into ecology and the environmental sciences. Another branch of this showed up in the early thinking about space settlement. Tsiolkovsky was aware that he needed to get oxygen to the space habitat he was envisioning at the turn of the previous century. And Bernal, in his work, The World, the Flesh, the Devil, which is from the 1920s, but sets out ideas about space habitats, overcoming material scarcity, cyborgs, and many other things. He's also talking about building enclosed ecosystems in space, which were then later popularized by Olaf Stapledon's fantastic science fiction novels, Last and First Men, and especially Star Maker. In the 1960s, Dandridge Cole, who was one of the key people in coming up with ideas about space settlement, started talking about macro life. His idea was that if you build a habitat in space, it needs to contain technology to keep you alive, but also an ecosystem. And actually, that entire habitat, with its humans, machines, and life, should be regarded as a kind of cell. Just like prokaryotic organisms merge together to form eukaryotic cells with different functions. The chloroplast in plants, the mitochondria in plants and animals, they were originally free living organisms that have now joined together to make something more effective. Similarly, a macro life could be regarded as a kind of eukaryotic life form. Smaller things come together. Indeed, this is very similar to some of the idea about many of the evolutionary transitions, but quite often you find moves from single systems that join up to become multicellular, or that you develop complicated organs, nervous systems, or ecosystems. But anyway, the macro life concept was basically saying we could create a new form of life, an evolutionary step that has an ecological niche, which is space, taking sunlight and asteroid material and turning that into more habitats, more life. Now, this, again, I can go on forever. I'm going to try to gently sidestep this rabbit hole, but it's absolutely fascinating. Also links up to early ideas about cyborgs, cybernetic organisms. Manfred Kleins and Nathaniel Klein pointed out that, well, the astronaut and his spaceship, they're in some sense a system. We should regard them as one organism. So they used the term cyborg from the science of cybernetics, control theory, and early information theory, seeing it as you actually merge the human and machine, because it's all about the information processing and the joint action. These cybernetic ideas are very relevant for the systems perspective. And I think we can see that we could talk about a cyborg ecology. In many ways, Earth's ecosystem has become a cyborg ecology because of interventions. I don't have the time to get into the fascinating stories about the concept of spaceship Earth, which again, as a metaphor, is fairly old. It actually goes back to Henry George's work in the 1870s, where he was thinking about Earth as a ship on the ocean. And George Orwell actually used the same metaphor in the 1930s, but then it became very popular in the 1960s when Adlai Stevenson used it as a metaphor in a famous speech for the United Nations. In that perspective, it's a nice, rich ship. It's well provisioned, but we need to steer it well, and we need to make sure everybody gets fed. But it has also, of course, been taken as a metaphor for, oh no, it's a fragile, small ship on a stormy ocean. It's a closed system. We can't get anything from the outside, and it's isolated. If something breaks, we will not get any help. Another way of looking at it is, of course, to say, this was especially stimulated by those epic photos from the Apollo project, where we suddenly saw that little blue marble on the velvet blackness of space, is that we have a unity of humanity and the biosphere against that vast hostile universe out there. We need to keep the flickering flame of life going. But one can also take the spaceship Earth as a view that, oh, we're on a spacecraft and it's not entirely working right. We better fix it. You can say this is our duty as the engineers to do something about it. You can find that, for example, in Isaac Asimov and especially Buckminster Fuller's thinking about it. So here we would say, okay, we have a life support system and it's kind of failing because we messed it up. We better be careful about it and repair it. Now you can critique this in various ways because to some extent, like I said at the start, the life support system we need is very different from the life support system a prokaryotic bacterium needs. They don't care if the Earth's surface is mostly desert, if they live down in the ground. Many of the deep ocean organisms don't care at all if the atmosphere has oxygen or not. But we certainly care. So there is also an interesting aspect here of decision. What kind of biosphere would we care to be about? Not just for our own sake, but for the biosphere. A biosphere full of single-celled organisms is a fine biosphere in some sense. except that we might say we would like to have coral reef too, please. We would actually want to have a biodiversity, that multiplicity rather than nice biofilms covering some rocks on there. So getting back to the planet B and space, it seems like if we want to settle space, we need to solve some problems. One problem is, of course, automated mining of low-grade ores. That would be actually quite useful here on Earth because we're running out of high-grade ores. And indeed, we have some things called landfills that are full of useful materials. We want automated manufacturing in space, and we want near-perfect recycling. That would be darn useful down here too, especially since our current recycling systems are not up to scratch. We also want to be able to build closed, stable ecosystems. And of course, we want to have non-fossil fuel power, and we want to have systems that are super robust. Now, if we have all of that, then we can certainly settle Mars and probably settle asteroids, which I think are actually a better place, even though there's less placeness in the asteroid belt than on Mars, where everything has a cool name out of a fantasy novel. But if you can settle Mars, then you can also settle Earth. In principle, you have perfect sustainability by us taking that Mars space and putting it in a parking lot here. You have in some sense, okay, it's close relative to the ecosystem around it, and we can keep on going forever with solar power. So we have in some sense solved sustainability, except of course, most of us probably wouldn't want to live isolated from the biosphere. Decoupling from the biosphere is great, up to a point, because we actually want to be connected to the biosphere. But that is partially a value judgment, partially an aesthetic judgment, but also partially robustness because it's useful to have a bigger system. And I think in general, there is this interesting problem that if we're coupled with the biosphere is also going to be partially, it can't escape the noosphere. Our ideas, our values, our ideas about what is good nature is going to affect it. And these are partially cultural, partially purely political. And there's going to be endless political battles about what kind of garden do we want? Do we want to have a garden, or should we rewild half of the planet? Are we going to allow people to add to biodiversity by adding new species? That seemed to be a good idea. There is quite a lot of interesting tensions here. You could say, well, maybe there are too many people. Yeah, but getting rid of people is usually the start of something very dark when you start thinking about it. So you still need to make it sustainable for a lot of people, and they're not going to accept it unless their standard of living actually are pretty good. It must feel luxurious and good and to be green. If it doesn't, people are not going to go green now. So there is a lot of interesting things here going on, but to try to summarize, we are a technological species. We have already made our own kind of shoddy planet B. It's kind of sitting on planet A and causing a lot of damage. But the cool thing is we can change planet B. It's the result of human action. Not always easy to change back. A lot of human structures are amazingly resilient, even when we ought to change them. But it is changeable. It is already changing rapidly, and we can actually adapt it. If we want to save the planet for the biosphere and humans, we need to work on that. Now, that means that space is kind of secondary. It's not a cost-effective way of reducing existential risk. On the other hand, it's a very useful aim. If you want to get the funding for building the radical ways of saving the ecosystem, you probably can't get it saying this is a way of helping sub-Saharan Africa. But it's amazingly easy, actually, to get the funding by saying this is going to be useful on Mars. There is some fairy dust of coolness from space that makes it easier there. Finally, this is a systems perspective. This leaves out other important questions, like people actually want things for themselves. They have rights. There are many issues about what methods we can do. If you take the very top levels of perspective on ecosystems and the human civilization, you might get some very disturbing ideas. So I think we have an interesting idea about that order that was mentioned before. What kind of ordering are we looking for? Because that is really what the concept of noosphere is about. It's the sphere of the mind. And as Karl Popper said, we are letting our ideas die in ourselves. We're essentially fast forwarding evolution in our heads and in our conversation, trying out various scenarios, rapidly looking at the ones that are promising, and then trying to implement them. And I think that kind of rapid evolution can be much faster than biological evolution and even the changes in the climate. And I think that is how we can make sure that planet B becomes more livable and compatible with planet A. And later on, we can spread it to planet C, D, and so on. Thank you.
Thank you. Is it time for planet B? Well, if you're contemplating it, go home now. The answer is no. But I would argue it is time for humans B, that we need to transform ourselves. We're biological creatures. Everything we consume pretty much is biological materials of one kind or another. And this is now somehow we need to break the bounds of our ecological evolutionary background so that we can live on the future planet and there still be some material, plant material, animals that eat the plant material left over for other organisms. So sustainability, we've just been hearing a little bit about and thinking about, but humans as predatory animals have not been really living sustainably on the planet for tens of thousands of years. The first waves of extinction of large mammals at the hands of human hunters started about 50 to 60,000 years ago in a big way. And we haven't stopped since. And the largest animals to the left, not all of them are domesticated, but certainly in terms of biomass, virtually all mammal material left now on the planet is our domestic animal. We foraged for plants, for roots, for fruits, for all sorts of things, and we use them for fibers, of course, as well. And we've gradually transformed from this foraging animal to ever more intensive farming systems, as illustrated by the rice paddies at the bottom. And what is this plant culture, agriculture doing? Well, what we're effectively doing is to maximize the fraction of the photosynthetic material on the planet that we can directly use or feed to our livestock. And so this landscape here may look denuded in some ways, it's kind of attractive as well, but a much higher fraction of that landscape of the plant material there is edible by us and our livestock than the top image. And then we've also commandeered energy in other ways. We've fed plant material to animals that we use as beasts of burden. We use charcoal and plant materials to produce heat and cook our food. We manipulate fire in different ways to produce good forage for livestock. And we also make use of plants, but just rather old plants that lived tens of millions to hundreds of millions of years ago, that through geological processes have ended up as today's fossil fuels. But all of that energy, when we burn it, that is being released, was fixed on this planet. It's solar energy fixed on this planet by photosynthesis. So here's the challenge. We're animals. Most of us are omnivorous. And even though there are growing fractions of people in some parts of the world, including this, who are vegan or vegetarian, total meat consumption is going up across the planet and is estimated to roughly double in the next 30 to 40 years or so. And our population, of course, is continuing to grow, 8 billion, soon 10 billion. And the greatest, before you sort of start saying, oh, we're consuming too much, the greatest increases in consumption, per capita consumption of food, are actually happening in the least well-nourished parts of the world, where I hope we would all think that this is actually quite desirable. So how on earth are we going to do this? We've got to double meat and dairy production and increase plant production as well, when we're already using 40% of the land surface for our agricultural production. We can't simply double that area. If you look at the world at the moment, a high proportion of the remaining non-agricultural land is either dry lands, deserts, or tundras, etc. And even climate warming is not going to turn this into the new corn belt of Siberia. So where's the remaining agricultural land we can use? It's the world's remaining tropical forests full of biodiversity. So this expansion potentially would come with really serious casualties. So here's an equation of life on Earth, total impact of humans, which you can do this for an individual item, you can think about it for food in general, you can think it could be for other materials as well. But it's effectively a multiplier, the number of people, that's going up, per capita consumption, that's going up, times the impact per unit of consumption. And that's where we have some flexibility to try and reduce that total impact. So here is a human. Our energy is basically coming from the sun. It's being fixed by plants. We're then consuming some of that plant material directly, but photosynthesis is incredibly inefficient. Rarely is it more than 1% in plants, and across the entire planet, it's 1/10 of that at best. We're getting some of that energy via our animals, but animal conversion of plant materials is only about 1/10 efficient again. So that's really, really inefficient. And then we're supplementing our energy supplies by ancient photosynthesis via fossil fuels. So how do we get out of this bind that whilst we need all this plant material and we're going through the animal and plant system, we are going to gobble up more and more of the biological resources of the planet. And there is no alternative to that. We're going to do it. There is going to be less left over for other biological organisms of the planet. Most conservation is about, what metaphor should we use? Rearranging deck chairs on the Titanic type of thing. It really is. We've got to break these flows. Well, for climate change, of course, we're in the process of doing it. It's frustratingly slow. It's probably going to take about a century, but we're going to use solar energy directly. Solar panels are 20 to 40 times more efficient than plants at converting solar energy into something we can use. Brilliant. Let's get rid of plants and put solar panels back. We can use the physics of gravity, of geological forces, nuclear energy, wind, etc., to produce the energy that we need. It's a slow transition. If I had any hair, I'd tear the rest of it out when I look at climate change politics. But we are in the process of doing this. It's going to take us about a century in total. The question is, can we break this? If you look at the International Union of Conservation of Nature and ask, what's the biggest threat to species on the planet? It's because of our land use and our food production systems, directly or indirectly. Can we get rid of this and somehow get our energy needs another way? And bizarrely and amazingly, incredibly, the answer is yes. These technologies actually sort of are starting to exist. So here we go. First thing we do, look, we will eat double the amount of meat. It's already taking up 30% of dairy. It's already taking up 30% of the land surface. We cannot double that. We just can't. How's it going at the moment? Well, actually, it's becoming more and more land efficient, meat and dairy production. How's it being done? We're keeping them in cages, we're keeping them in sheds and crowded conditions, keeping them in feeding lots, and we're growing the plants more efficiently and then bringing it to them. So we kind of can do it, but it comes at the cost of reduced freedom of those animals, increased cruelty. So it can be done. It's starting to be done. Tissue culture was developed mainly in medical circumstances, of course, but you can take stem cells, start to initiate their dividing. You can, in basically biochemical vats. You can get these cells to grow and then produce cultured meat. You can initiate processes within cells so they produce milk and other dairy products and foods. There's over 100 companies involved. There's lots of venture capital going into this, but there's no policy reaction or response at the global level to oversee, control, or manage it. But this is now happening, but we do need inputs, of course. You don't get nothing from nothing. So we do need carbohydrate sources, etc., to produce the system. And of course, we're going to do it with renewable and clean energy. Step 2 is to upscale microbial production. There's a huge range of microbes that can be grown in these sorts of factory conditions. We already get some things like wine. Alas, we might get more products like Marmite. But what we can again fuel the whole of this system using physical energy rather than it being largely plant material. And of course, in these sorts of things already, there's thousands of companies doing this. You go around the supermarket and at least somewhere in the process, factories are involved in many, many of the products that we might buy. And of course, this sort of material can also be used as feedstocks for the cultured meat and dairy production. Step 3, really exciting because, of course, carbohydrates are just carbon, hydrogen, and oxygen. And we've got too much CO2 in the atmosphere, so we take some of that out without much problem. We've got rather a lot of water on this planet, thank goodness, and has been pointing out, it's rather fortunate that most of it's water, while most of it's in its melted form. So this is really excellent. So we can use this energy to extract CO2 from the atmosphere, desalinate water, and bang, via a sort of formaldehyde process, you can generate sugars, you can generate simple carbohydrates. We might eat some of that, but again, it will then go back into this can be the fuel of those cultured meat production systems. And then step 4, I don't know whether there'll be much of this because we will have released so much land by those first 3 things that there'll be plenty of room to grow our vegetables in fields. But on the other hand, I drove past a what do they call now, fulfillment center on my way in this morning. Huge factories are going up, and you can have dozens potentially of layers of plants on top of one another. Optimum heat, optimum light intensity, optimum wavelength, maximizing growth, and you can grow these things all the year next to where the markets are. You can cut out most of the transport system. So effectively, there we go, is that if we were to adopt these, and I'm still assuming here that something like 5% of our agriculture is of our meat production, let's say, is still going on this conservation grazing land. So we haven't got rid of all of the animals. But we can get down to something like 6 or 7% of the land surface, abandoning more than 80% of agricultural land. It's really doable. I think because of all cultural issues, this is probably going to take more like 150 years than 100, but I actually think it's going to happen. I think this is the future of our food production system. So, well, I might not be the specimen to start talking about let's getting physical, but we can bypass a lot of photosynthesis. We can bypass living animals, and we can energy, just as was described so nicely for the nitrogen that we have in our bodies today, that most of the energy that we use can actually come from physical trapped energy rather than through photosynthesis. And if we do that, there's considerably more plant and animal material left over in the planet to be shared amongst the world's biodiversity. So finally, I'd like to thank members of the Leverhulme Trust who sort of funded my thinking on this, colleagues at the Leverhulme Centre for Anthropology and Biodiversity at University of York, and particularly contributors to Pixabay, who produced those nice cartoons that I stuck out on some of those slides. So thank you very much indeed.
Hello. We are having our next three panelists. Professor Martin Rees is a cosmologist and astrophysicist. He is the UK's 15th Astronomer Royal. He was a Master of Trinity College, Cambridge, from 2004 to 2012, and President of the Royal Society between 2005 and 2010, and remains active in the fields of astronomy and astrophysics, with over 500 research papers to his name. This erudite polymath has also made contributions to the origins of cosmic microwave background radiation, as well as to galaxy clustering formation. His studies of the distribution of quasars led to the final proof of a steady state theory, and he is one of the first to propose that enormous black holes power quasars. Professor Rees has been a recipient of many accolades, and we at NoRCEL are honored, and he has been able to join our forums to expound the question of, is it time of a planet B?
Exobiology is a burgeoning research field because there's now a real prospect that in a decade or two, we'll have the capability to detect biosignatures, non-equilibrium atmospheric chemistry, vegetation, etc., on nearby exoplanets. But of course, what's most interesting of all would be some techno-signatures. And I'm going to speculate about those prospects, but with diffidence. I'm not an expert. And I think the science fiction writers, and maybe Anders Sandberg, can tell us more. If intelligence emerged on another Earth-like planet, we've no idea of its nature or motives. So in these remarks, I'm going to offer conjectures on our Earth's post-human future, where at least we know something about the psychology of the currently dominant species, and we can make some guesses about future technological trends. So here are my guesses. By the 22nd century, some thrill seekers may have established bases independent of the Earth, probably on Mars or on asteroids. Elon Musk, by the way, says he wants to die on Mars, but not on impact. It's a realistic goal. He's only 51 now, and alluring to some. But don't ever expect mass emigration from the Earth. Here I disagree with Musk, who advocates rapid build-up of large-scale Martian communities, because it's a dangerous delusion to think that space offers an escape from the Earth's problems. We've got to solve them here. Coping with climate change may seem daunting, but it's a doddle compared to terraforming Mars. Indeed, nowhere in our solar system offers an environment even as clement as the Antarctic, the ocean bed, or the top of Everest. There's no planet B in our solar system for ordinary risk-averse people. But we and our progeny here on Earth should cheer on the brave space adventurers on Mars. That's because they will have a pivotal role in spearheading the post-human future and determining what happens in the 22nd century and far beyond. This is why these pioneer explorers will be ill-adapted to their Martian habitat. So they'll have a more compelling incentive than us on Earth to redesign themselves. They'll harness the super powerful genetic and cyborg technologies that will be developed in the coming decades. These techniques will, one hopes, be heavily regulated on Earth on prudential and ethical grounds. But the settlers on Mars would be far beyond the clutches of the regulators, and we should surely wish them good luck in modifying their progeny to adapt to the hostile environment. And this might be the first step towards divergence into a quite new species. So it's the spacefaring adventurers on Mars, not those of us comfortably adapted to life on Earth, who will spearhead the post-human era. Organic creatures need a planetary surface environment. But if post-humans make the evolutionary transition to fully inorganic intelligences, electronic beings, they won't need an atmosphere. And they may then prefer zero-G, especially for constructing massive artifacts. So it's in deep space, not on Earth, nor even on Mars, that non-biological brains may develop powers that humans can't even imagine. We're perhaps near the end of Darwinian evolution. The technological evolution of intelligent entities, what I call secular intelligent design, is only just beginning. And that'll happen fastest away from the Earth. The timescales for technical advance are measured in decades or centuries. That's thousands of times faster than the timescales for each stage of Darwinian selection, which led to our emergence. More relevantly, each step of technological evolution could take less than a millionth of the vast expanses of cosmic time lying ahead. So the far future outcomes of technical evolution could surpass humans by far more than we intellectually surpass slime mold. What would be the motivation of electronic post-humans if they become fully autonomous entities? We've absolutely zero ideas. Think of the variety of aliens in upmarket science fiction. They could be expansionist, and this seems the expectation of most who've thought about the future trajectory of civilizations. If that's right, then even if life had originated only here on Earth, it need not remain a trivial feature of the cosmos. Humans could jumpstart a diaspora whereby ever more complex intelligence spreads through the galaxy, far transcending our limitations. The leap to neighboring stars is just an early step in this process. Interstellar and even intergalactic voyages would hold no terrors for near immortal electronic entities. This expansionist scenario would have the consequence that our descendants would become eventually conspicuous. So any aliens out there would become aware of us. But the great question, of course, is ET out there already? Are there, as in models discussed by Olson and others, other expansionists whose domains may impinge on ours? We all agree that we don't know. The emergence of intelligence may require such a rare chain of events, like winning a lottery, that it hasn't occurred anywhere else. This will disappoint SETI searchers, but if we are not alone, what evidence would we expect to find? Suppose that there are indeed many other planets where life began, and that on some of them, Darwinian evolution followed a similar track to what's happened here. Even then, it's highly unlikely that the key stages will be synchronized. If the emergence of intelligence and technology on a planet lags significantly behind what's happened on Earth, because the planet's younger, or because the bottlenecks have taken longer to negotiate, then that planet would plainly reveal no evidence of ET. But around a star older than the Sun, life could have had a head start of 1 billion years or more. The history of human technological civilization is measured in millennia at most, and it may be only 1 or 2 more centuries before humans here on Earth are overtaken or transcended by inorganic intelligence. But that will then persist, continuing to evolve on a faster than Darwinian timescale for billions of years. Organic human level intelligence is therefore generically just a brief interlude before the machines take over. So if alien intelligence had evolved similarly, we'd be most unlikely to catch it in the brief sliver of time when it was still embodied in the form of a flesh and blood civilization. Were we to detect ET, it would be far more likely to be electronic, where the dominant creatures are no longer flesh and blood, and maybe aren't on planets. So we must reinterpret the lifetime factor in the Drake equation. The lifetime of an organic civilization may be millennia at most, but its electronic diaspora could continue for billions of years. And this, of course, enhances the chance of detecting some manifestly artificial phenomena. The focus of SETI has, of course, been on the radio part of the spectrum, but of course, we should clearly explore all wave bands, optical, X-ray, etc., and also be alert for other evidence of non-natural phenomena or activity. One might seek evidence for artificially created molecules, such as CFCs in an exoplanet atmosphere, or for massive artifacts like Dyson spheres. And it's worth looking for small artifacts within our solar system. Maybe we can rule out visits by human-scale aliens, but if an extraterrestrial civilization had mastered nanotechnology and transferred its intelligence to machines, the invasion might consist of a swarm of microscopic probes, which could have evaded notice. It's even worth keeping an eye open for especially shiny or oddly shaped objects lurking among the asteroids. One might then ask, what about the Fermi paradox, which argues that because we've seen no evidence, aliens probably don't exist? We must rethink the Fermi paradox too. That's because Darwinian evolution favors intelligence, but it favors aggression too. In contrast, future evolution, what I call secular intelligent design, need not favor aggression. So our remote post-human descendants, and indeed the overwhelming majority of technological advanced aliens, may be quiescent and contemplative rather than expansionist. So Fermi's argument against there being aliens becomes much weaker. And just a few final comments about the far distant future. All I've said now is consistent with the laws of physics and the cosmological models as we understand them. But we should surely be open-minded about the possibility that there's much more that we don't understand. Human brains have changed little since our ancestors roamed the African savanna and coped with the challenges that life then presented. And it is in fact remarkable that these brains have allowed us to make sense of the quantum and the cosmos, far removed from the common sense everyday world in which we evolved. Scientific frontiers are evolving fast. Answers to many current mysteries will surely come into focus. But we may sometimes hit the buffers. There may be phenomena crucial to our long-term destiny that we're not aware of, any more than a monkey comprehends the nature of stars and galaxies. So physical reality could encompass complexities that neither our intellect nor our senses can grasp. And some electronic brains may have a quite different perception of reality, nor can we understand their motives. That's why we can't assess whether the great silence signifies their absence or simply their preference. So just to conclude, conjectures about advanced or intelligent life are far more shaky than those about simple life. I'd argue this suggests three things about the entities that SETI searches might reveal. First, they will not be organic or biological. Secondly, they may not remain on the planet where their biological precursors lived. But thirdly, we won't be able to fathom their intentions. That will be a mystery. Thank you very much for listening.
Well, I'm going to introduce you to Dr. Jack Lissauer. Dr. Lissauer has several and special distinct interests, which includes planet formation, detection of extracellular planets, assessing abundance of habitable planets, rotation of planets, resonances, and chaos, and planetary rings and moons. If we consider the core of the Blue Earth Project 2023 question, it could easily be reinterpreted as, should we consider extraterrestrial settlement now, and where do we sow, where do we sow our future? Dr. Lissauer is well placed to offer a response to the question of humanity's destiny in this unfolding universe.
Hi, I'm Jack Lissauer from NASA's Ames Research Center in California, and I'd like to give you a little introduction to habitable planets, or what little we know about them. And I'm going to be talking about two topics today. The first one will be about NASA's Kepler mission, on which I was a co-investigator. And Kepler discovered many thousands of planets by observing them transiting in front of the disks of their stars. And with this, we were able to estimate how common many types of planets are, including some types that aren't too different in size and conditions from our own Earth. And then, after that first part of my talk, I'm going to briefly address the central question that we're dealing with today about Planet B, and specifically the portion of what is the best choice if we must go to Planet B. Here we see a diagram of planetary transits. On the left, we see a top view and a side view of a planet orbiting a star and going in front of the stellar disk from this side view at the bottom. On the top right, we see what the spacecraft sees, the amount of light from the star, which periodically drops for a short time every time the planet makes one orbit around the star and goes to a position where it's blocking part of the stellar disk. What's actually being seen in terms of the data that we can get back on this is that the brightness of the part of the camera on which that star's light falls goes down for a period, generally a few hours, once every orbit of the planet. Now, this, of course, doesn't happen unless the planet happens to go in front of the star as observed from the telescope, and that's a small fraction of the planets. So Kepler was designed to observe over 100,000 stars almost continuously, and was able to do so for a period of about 4 years. Here we see on the left a light curve from one of the most interesting planetary systems that Kepler found, Kepler 11, a system that has 6 planets that periodically transit their star. The light curve here has been annotated with colored arrows showing when those transits occur. And on the right, we have an artistic rendition of that triple transit event near the end of the time series data shown on the left. This is actually much more science than most science art is, because it shows the planets that were transiting during the transit. But there is some artistic license used in the sense that the planetary sizes were increased by a factor of about 2.5 relative to that of the star for increased visibility. And the fact that planets are much smaller than stars and therefore only cause a very small dip in the observed stellar brightness is the reason this experiment was done from space above the variability of Earth's atmosphere. Kepler found over 4,000 planetary candidates, the vast majority of which are likely to represent true planets. Here we see them plotted on the plane of planetary radius versus orbital period. Now, it's much easier to detect large planets and planets closer in, because the planets closer in, more chance that they will transit across the face of their star, plus more transits during the 4-year period. So these observations are not a representation of how common each type of planet is. However, you might notice over towards the lower right, there's a tiny image of the planet Earth. That's where Earth would fall here. And you see there aren't many planets there because such planets are so difficult to detect. Now, we can correct for the difficulty in detecting smaller and longer period planets and look at how common planets are in this plane in terms of the percentage chance that a planet would be in that range, specified range in orbital period and planetary radius. And this is around stars that are roughly like the Sun. And you can see that the green, which represents much more abundant planets than the red by a factor of 100 to 1,000, is there mostly for the longer period and relatively small planets. But there's a lot of gray area where we don't have enough data to estimate with any degree of confidence how many planets there are there. And that happens in the upper left of the diagram because very large close-in planets are definitely quite rare, and in the lower right where again, that little photo of Earth lies, where planets are very difficult to detect. So, transitioning towards the topic of the day, would an exoplanet be suitable as a planet B, a place that we could move to if we need to? Well, first of all, no known exoplanet is a bona fide Earth analog in terms of being close in size, orbital period, and orbiting a star similar to our Sun. Characterizing an exoplanetary Earth analog for human habitability would be much more difficult than just discovering one. We haven't discovered any yet. And if it has adequate oxygen, that suggests there's life analogous to that on Earth, and it could well be inhabited by microbes that could do very nasty things to anybody who tried moving there and living there without spacesuits all the time. Beyond that, getting to a planet in another solar system would be extremely difficult. It's well beyond any technology we have. And it's also difficult in terms of fundamental physics. Just getting the energy to get all that mass out of our solar system and then slow down and landing onto a planet. And therefore, it's not a viable alternative if we need to go to some type of lifeboat in the foreseeable future. And it's probably never going to be a viable possibility for large-scale immigration, such as that which the citizens of Ireland did in very large numbers during the potato famine. So, what is to be done? First of all, we have a habitable planet right now. Let's keep it habitable. I'm not there in person today, largely because of the coronavirus and the difficulty it is causing here on Earth. But if not for COVID, I would only actually have gone there to be in person with you if I'd been able to do several other things on my trip, because I feel that it's inappropriate to take long trips for short periods of time, given its negative impacts on our planet's environment. Okay, so the right thing to do is to take care of our planet, and there are many ways that we can do that. But what if something really goes wrong and we need to go somewhere else? Where would we go? Well, I have here some photos of various solid bodies in our solar system. And addressing this a little more, our two planetary neighbors, Mars and Venus, they each have issues. Venus, it's the planet most like our own in terms of its size, mass, density, etc. But the atmosphere is much thicker. It's hot enough to melt lead on the surface and very high pressure. It would not be suitable for going to. Mars, people have talked about colonizing Mars. But if we really want to use Mars as a colony, it's the place that would be the planet that would be most easy to terraform, or least difficult to terraform, to make habitable. But it would be much, much harder to terraform if it were inhabited, because the construction site for terraforming would involve bringing lots of material there, heating things up. Much, much more difficult if we had people living there. So what are our options? Well, actually, I think our best option would probably be our moon. It's the closest, easiest to reach. People have actually been there already. The poles have very favorable illumination so that you can get near constant solar power, and you can go very easily to areas that are sunlit at any time. And it has enough gravity for walking around, not for holding an atmosphere, but if you're in a contained space, you're at least not floating around. You're living in a environment that is at least a little bit like what we've evolved to live in. There are other options. Asteroids and the small moons of Mars are fairly easy to reach, easier to reach than any other planets. But they have very low gravity. Not clear if that's really a good long-term strategy. And Mercury's poles have some of the same advantages as the moon's poles, including having ice, water ice that could be mined, and favorable illumination. But it's much harder to reach, and you get a little away from the poles and you get much larger extremes. So to conclude, we should be taking care of Mother Earth. There is really no other good option. And if a lifeboat is needed to save humanity, the moon, or perhaps one of the asteroids or Martian moons, probably the least awful alternative. Thank you for your attention, and I look forward to participating in the discussion with you this afternoon.
Finally, I introduce you to Professor Kathryn of York University, Canada. Primarily, Denning's research focuses on scientific search for life in the universe, social and ethical issues in space exploration and colonization, together with the role of archaeology and the archaeological past in relation to the present. Professor Denning is an ideal candidate for looking to provide an answer for the question of, is it time for a planet B?
Hello, I'm Kathryn Denning. I wish I could be there with you in person or live today, but I'm in Canada, and also I got COVID for Christmas and I'm still recovering, so I'm only able to send you this recording. But I do send my warm greetings to you all and my sincere thanks to the organizers, sponsors, and my fellow panelists. I particularly wish I could be there because I did my PhD just up the road in Sheffield 20 odd years ago, and it would be really lovely to be back in the neighborhood. But since I'm not there to wave at you, here are a couple of pictures from my spacey anthropological adventures, so you know who I am. This is me with a telescope that Percival Lowell used in his observations of Mars over a century ago when he was convinced he saw canals, an instrument which kickstarted our modern age's extremely peculiar relationship with that planet. And that is me trudging through the Utah desert in a fake spacesuit at the Mars Desert Research Station, an experience I highly recommend. So, hello. My job as an anthropologist is to make cultural observations. They're not necessarily the ones you might expect to hear. You might perhaps like it best if I told you how to get everyone together to do what we need to protect Earth, also known as Planet A, or if I told you how to create sustainable, equitable space settlements that would make viable the idea of a Planet B. But I won't be doing that today. What I'm going to do instead is try to unpack the question, is it time for Planet B, a little bit, and try hard to give you some additional ideas to think with as you continue to ponder and discuss with our other panelists today and beyond. So here is my answer to that question. Is it time for Planet B? Absolutely not, and definitely always at the same time. It's both. Briefly on the absolutely not side, reiterating just a few principles here so that we're all standing on solid ground as we contemplate the stars. I think most of what I'm about to say is not controversial. First, when we hear exciting news about exoplanet discoveries and those very distant planets are characterized as Earth-like or habitable, we need to be aware of what those terms actually mean in astrobiology. They don't necessarily mean really Earth-like, and they certainly don't mean habitable for us. Second, we simply do not have the capacity to get to an exoplanet yet. We do not have interstellar travel, and that's not just coming from me, your friendly neighborhood space anthropologist. Rather, that's coming from breakthrough propulsion experts like my colleague Mark Millis, who recently did a review of all the possibilities for NASA. We don't have interstellar propulsion now. We're not going to have it soon. We might never have it. And we're probably going to need some new physics. There are some really smart people working on this, but we're not there. If we were only sending tiny electronics, that could be easier and might be achievable within a few decades, but not sending humans. Also, humans haven't even been further than the moon yet. Yep, there's a lot of talk and planning for Mars, but it's not happening yet. And we need to foreground and remind ourselves of this because our popular culture tells us constantly and vividly that we have been to all those other places, that we have been beyond our own star system, that we have settled Mars, the moon, and the asteroid belt, etc. And we need to remember that those things really are fiction. Also, there actually aren't good reasons to believe that humans can survive very long space voyages, survive on colony ships, or reproduce successfully off Earth. And there is plenty of evidence suggesting that we can't. Definitely, people are doing some really interesting research, but it's still really early days for all of that. So basically, this leaves us with our own solar system and really with Mars. And as for Mars, we don't know yet that Mars is dead, which raises a lot of questions. The astrobiology research needs much more time, ideally before human boots, land on that planet. The prospects for human survival on Mars for more than brief periods are really not encouraging, and certainly worse than on an even seriously degraded Earth. So this is not a fix. A self-sustaining, fully independent settlement on Mars is not really feasible yet. And even if it was, it might be very cool, but I think we can ask whether and how it would really benefit the vast majority of humanity. And more on that a little bit later. So briefly, on the definitely always side, we have this conundrum, right? So we can see so much further than we can go. And that's actually rather confusing. With screens and immersive technologies, we can now experience flying between stars and walking around on other planets in ways that previously were only possible in dreams and daydreams. Culture doesn't obey the laws of physics. And we have in our culture by now a pretty entrenched sense of escaping to other planets being an option. There is this cultural notion of a viable planet B, even if it's not scientifically substantiated. And I just want to underscore that this actually has ancient roots. Many human cultures have had notions of other worlds up in the sky, not exactly planets as we understand them today, but other dimensions, other places of some kind where spirits live or other beings, or maybe even where we go when we die. those other worlds have, in a sense, started to overlap with our new scientific reality of exoplanets. Remember, literal exoplanets are a very new reality. Their existence hadn't been confirmed until just several decades ago. Of course, they were always there. We just couldn't see them. Obviously, with the new amazing telescopes, scientists keep on discovering more and seeing them using different methods and characterizing them in greater and greater detail. But that's very, very recent. So all that science fiction before the 1990s and all the older ideas about other worlds, it was fiction. It wasn't actually about real exoplanets. Early ideas about other worlds were purely journeys of the imagination. But so we have this crazy intersection now between our cultural notions of other worlds and the science of other worlds. These ideas are now intertwining, hybridizing, and producing this really, really vivid fiction about other worlds, but it's not real. And it's important to know that scientific searches for exoplanets originated as part of the search for other life in the universe, not as a search for a new home for our Earth life and humans. It's about the possibilities elsewhere in the universe, the possibilities for other life, not new destinations for ourselves. But exoplanets have become appropriated into our own story. It doesn't make a lot of logical sense in the short term, certainly, but space agencies do need to make their work relatable to a wide audience. And so it's entirely predictable that we'd end up with artists' hyper-real visualizations of exoplanets, and with things like NASA's famous Exoplanet Travel Bureau posters. But I think one of the reasons all of this is so compelling right now is because we need hope. And on that, I have some kind of further thoughts about how we can be thinking constructively and realistically about space and human futures. So first, I think we should use the power of hope well. I think Planet B is compelling to many people today because, Earth's issues can feel overwhelming. There are a lot of grounds for immense concern. But I think hope does its best work when it's strongly tethered to facts. So I think it's good to hope, first and foremost, for things that we can actually achieve here on Earth and in the near term. I'm not saying to stop thinking about space, but keep it in perspective and be realistic about it. If we're concerned about existential risks to Earth, then we need to mitigate those here for our own species and all the others that are here. Right here is where we make our stand. We need to recognize that space development and expansion are going ahead, regardless of our deliberations here. I don't get a vote on the space policies of all the nations of the Earth, and neither does anyone else here. Similarly, I'm not expecting a call from the highest echelons of the major space corporations. So I'm not personally going to be an architect of all this, and probably most of us here today aren't either. So, does that mean that our only role is as passive spectators? I hope not, because I think it's really important to consider ourselves as citizens of the solar system. And if, like me, you would prefer a peaceful, multilateral, equitable management of the space near Earth, then we have to speak up. Related to that, there's the question of who exactly is we? Discussion of space and the future often involves a rhetorical we that encompasses all humanity or our entire species. But I think it's time to think differently about space. What if there is no big we here? For the foreseeable future, only a very few human beings will have the capability to launch or act in space. That tiny contingent of humans does not include me. I have opinions, but I don't have a vote about what they do. And that's true for the vast majority of us. And that matters because when a space agency, space advocacy group, space corporation CEO, for example, says we should do X or Y in space, they're using traditional rhetoric that encourages audiences to think that we, the rest of humanity, are a part of what they are doing. Clarity on this matters a lot now. As multilateralism is either faltering or collapsing, the capabilities of private actors are accelerating and the likelihood of unilateral actions increases. There are a multitude of different interests in space and a multitude of ideologies and capabilities, not one unified we. Related to this, it's certainly true that many of the technologies that are useful for space environments would be useful for Earth, and also that space-based technologies can be extremely helpful for environmental monitoring. Absolutely. But we also need to be mindful that some space-related technologies are not merely civilian or humanitarian. Technologies are always multi-purpose, always have been, and always will be. For my part, I will never forget, for example, being at an interstellar conference 12 years ago and hearing a prominent member of the American defense community saying that he was there because what's good for space is good for the American warfighter. His words. And of course, this is true. And Neil deGrasse Tyson mentions a similar issue in his book, Accessory to War, about what he calls, quote, the unspoken alliance between astrophysics and the military. So that's something that we should be bearing in mind. And by the way, the books that I'm mentioning, I have a reference page at the end of my slide deck that you can look at. So in light of that, we need to think about various risks to Earth engendered by space. So the opening of outer space is often portrayed as simply positive. Space is a realm of possibility, wealth, power, freedom, innovation, constructive diversification, frontiers, everything we could ever dream of. But there are some significant potential downsides. In his very thought-provoking book, Dark Skies, political scientist Daniel Dewdney outlines the risks of space militarization and expansionism. This is not an anti-space book, but rather it outlines what he calls an Earth-centered pro-space agenda focused on nuclear security and environmental protection. It is really worth considering. On that note, it's also worth mentioning that space launches do have significant impacts on Earth environments. They're not neutral. So all of this means, I think, that we need to think about which aspects of space exploration and use we really support and which we don't, or rather, which ones you support and which you don't. Maybe you're like me and you are a huge fan of telescopes and of robotic exploration for scientific study, but you don't really see the point currently in a significant human presence off-world. Or maybe you want to be a space tourist. Maybe you want to move to Mars. That's up to you. But as a citizen of the solar system, it's time to think about it carefully if you haven't, and to disentangle it all, because these different engagements with space have vastly different implications. And also, if you look at the space policies of different nations, you might be surprised, and not necessarily in a good way. If you don't think that space should be first come, first served, you should probably say so now. Related to this, it's good to carefully consider where you think the edges should be. So, for me, I don't particularly want humans to become extinct, but neither do I think it's worth preserving our species at absolutely any cost. So let's say hypothetically that the only way to preserve our species is in a militaristic, dictatorial society with tiny settlements in completely inhospitable places in our solar system, with rigid hierarchies and compulsory labor, reproduction which is intensely regulated and enforced and requiring major technological and medical intervention, and environments for children which are completely unnatural and absolutely no way out. Would that be a version of our species which is worth saving? I think we get to ask that question. And if your answer is no, then it's good to think about how to avoid that. Also related to this, I don't think we should be sure that what happens in space will stay in space. There are ideas afoot currently about genetically modifying humans for space environments and for reproduction with frozen embryos and ectogenesis in androids. I see papers of this nature in the refereed scientific literature on quite a regular basis that come across my desk quite often. Proponents justify these extraordinary ideas, which do contravene most current medical ethics, because they regard space settlement as absolutely imperative. But the current ethical rules are there for good reasons, and we should recognize that their erosion will come at a cost. And more than this, ideas and technologies don't just migrate in one direction. If something developed for space can be used for strategic advantage on Earth, it probably will be. So, are you okay with that? Related, again, I would also question research which induces suffering to sensate beings in the present in the name of human futures. Our primate relatives have also already suffered far too much for the sake of human spaceflight dreams. Much of the early research was horrific, and it could have been much less so if the 1960s space race hadn't made it so artificially, politically urgent to get human beings into orbit. So I would want to see really strict ethical guidelines stay in place as research about humans in space progresses. But if there's an artificial rush to it, then chances are those guidelines will be eroded or thrown out the window. So, finally, Earth is our home. There are other planets known and as yet unknown about which we may learn wonderful things. But unless there are some incredibly improbable surprises, there isn't a real planet B for us. But still, alternate worlds will continue to proliferate in culture and imagination, growing ever more immersive and vivid and believable. And some people will continue to pursue space expansion in reality for a variety of reasons. What all this requires of us is, first, an unwavering and creative dedication to our home world and the well-being of its biosphere and its humans. Second, simultaneously, a rigorous and careful attention to the different uses of space and every reasonable effort to ensure multilateralism, peace, human rights, equity, sustainability, and fair consideration of the consequences for Earth and its inhabitants as some humans and their technologies move outwards. Star Trek famously suggested that we will boldly go, but I've always preferred the words of my colleague William Kramer, who suggested instead that we humbly go. So thanks for listening. I hope you have a wonderful discussion over lunch and this afternoon. I do wish I could join you, but I do hope to catch you another time. Meanwhile, I'll just leave you with a final slide. If you're interested in more social science of outer space and more exploration of some of the issues that I've mentioned, here are some references which you could explore. Take care.
Welcome back. So you've heard all the interesting initial thoughts from our panelists. So now we have everybody on the panel except for Kathryn Denning, who unfortunately became the victim of some coronavirus that is still doing the rounds. So that's a pity, but we have to live with that. For starters, you've heard presentations this morning. What do you take from it? What were your impressions and how would you reflect about what you've just heard? We'll do a round and we start with Erika.
Well, I really enjoyed all of the talks, of course, and especially this morning, I was intrigued by, even though we came at this from several different angles, there are a lot of shared themes. One that I was thinking of for the first session of talks is we all essentially answered the question with a no, or at least a qualified no, and then focused on technologies or social improvements that would actually be useful or even necessary in a space environment, but would also be useful here on Earth. And I think this is something interesting about studying the concept of a planet B or space colonization, space settlement, is a lot of the ideas that you come up with are useful here. It's all about how humans can live better with their environment. And so that includes things like how to get along with each other in space or on Earth, how do we break away from the shackles of photosynthesis, and how do we develop our technosphere in a way that doesn't damage the biosphere that it's sitting on top of. And so I thought those overlaps were really interesting, because I always find that getting people to think about space gives them a certain psychological flexibility that lets them consider radical things for living here on Earth that they otherwise wouldn't. Something about being in that sci-fi science fiction context in their head lets them really imagine things that they wouldn't otherwise think of as being feasible on Earth. And I think that's a really powerful tool, whether or not you're actually going to build a planet.
Anders, you look like you want to reply immediately.
Well, no, I'm really agreeing here, and I think it is interesting. I was thinking about what in my circle we talk about near mode and far mode. When we think about the future, there is one kind of future like how am I going to get to the train tonight, and what am I going to do on my holidays and for retirement, which is relatively me-centered and relatively here and now. It's also quite rich. And then when we talk about the future, we can also talk about the future, which is a bit like a movie. It's what you see on television. This is the much more story-like thing. It lacks detail, and it's not about me personally. And in psychology, we call this construal levels. There are different forms of construal levels, not just about far in time, but also far away in space or in social space, etc. And we tend to think about things differently on these different levels. And one of my hang-ups is, of course, that quite often we do think very freely and big about the future in space. And I think that's great. And then people are very bad at bridging that over to the actual thing, using that to think freely and openly about what we do next Tuesday. Because quite often people separate these domains entirely from each other. So the future is entertainment, which is real annoying if you're like me as a future studies person, because I want some of what I'm saying to be taken seriously. That you actually want to link them. And it used to be that space was a very effective way of linking it. In the 1960s and 70s, mankind's future was in space. And given that people assumed this, and there is, of course, a lot of fun anthropology to talk about here, that actually allowed a lot of imaginative ideas to even move into the mainstream. The problem we have right now is that after long hiatus, people have usually relegated space to that far realm. It's not part of reality. You can still think freely about it, but what you do next Tuesday, what do you do about climate change? Suddenly suggestions become much more pedestrian, and that probably doesn't work if we want to fix climate change or our food system or setting up international governance. So maybe a new space might help bridge this, because obviously the rockets are being launched and landed. We can see satellites while standing outside in the night and so on. But I still think there is this interesting gap about how we bridge from the free and open futures, which are very important both for hope and for thinking about radical stuff, over to what we actually do here and now and on next Tuesday.
Chris.
Well, I think to some extent, I'm sort of optimistic that everyone is focused on how we need to make our lives on this planet somewhat more sustainable. I'm simultaneously slightly depressed by Martin. Sorry, Martin, the idea of all of these machines flying off into space with either a higher or lower level of intelligence and replication, because I think, unlike Martin, I believe that survival of the survivors will operate just as much with machinery as it will with living life forms, because those that replicate fastest will increase most, spread the most, and even in biological mutualisms of cooperative arrangements, virtually all of those are designed to outwit other combinations of organisms. They're not out of some sense of goodness. And so I think these things that disappear off into space are just as likely prone to become, as it were, malevolent to other things, and that it might not be so many centuries into the future that they're coming back on Earth and raiding it for anything that might be left.
So, Martin, I'll let you reply to that.
Hello, can you hear me?
Yes.
Okay, yes. Well, can I just say I'm fascinated by what we've heard this morning. I'm really sorry, incidentally, that I don't think the audio on my talk was very clear, so I hope you could hear some of it. But let me just say, I think one thing we've got to do is not conflate very different expanses of time in the future. People don't realize that the time humans have existed on the planet is about one part in a few thousand of the age of the planet, etc. And Darwinian evolution takes that length of time, but technological evolution is 1,000 times faster than Darwinian selection. And in answer to the last challenge about these post-humans who I speculated might not be flesh and blood, but might be electronic, then of course, if they're electronic, then they're near immortal. So they're not deterred by long voyages. But also, although the scenario you just mentioned about them coming back to destroy us is possible, I think there's a more benign idea, which is that whereas Darwinian evolution favors aggression as well as intelligence, this future evolution, which I call secular intelligent design, need not favor aggression. And that's why in the far future, the entities that are most intelligent may be just leading contemplative lives. And this is relevant, as I said, to the Fermi paradox, because it could be that there is a lot of intelligence out there, but it's not in the aggressive form that makes it so conspicuous. So I just think we've got to realize that the time lying ahead before the Earth dies is longer than the 4 billion years it's taken for us to evolve from the primordial slime. And so we can't conceive what those future intelligences will be like, but we've got to plan a bit longer. If I could come in and ask another question,
Sure.
while I have the floor, going back to what we heard about the Kepler spacecraft and detecting planets. One thing which I'd like to ask there is, what are the prospects if you look 100 years ahead? And in particular, I mentioned in my book the idea that a wonderful target for 2068 would be to have an imaged exoplanet, resolved image. And naively, that would require a baseline about the size of the Earth in the optical or something like that. But to have that by the centenary of the famous Ed Anders Earthrise picture would be a really inspiring goal. And I'd like to ask if you think that we will ever get detailed images of exoplanets, even though going to them is a post-human enterprise, not a human enterprise.
Well, I think we will get detailed images. How detailed in the 2068, I'm not sure. It's not clear that going there might not be by humans, but there are ideas of robots now, and it might well be that by the end of this century, one can send a robot there at whatever, a tenth the speed of light or something like that, and get a signal back. So I think we'll be able to get information there.
Yes.
But finding out whether a planet is really habitable is maybe beyond, or habitable for people, is certainly very complicated, because even if you see life like us, you don't know that the biosphere doesn't contain something that would be toxic to us.
No, I think the idea of us going there is rather crazy. I mean, the idea of sending a small probe, where it's been talked about with a straight face by Joran Milner's breakthrough people, talking about a laser accelerated probe at 0.2 of the speed of light, but that's only a few grams. All it would do is send back a few pictures, so it won't tell us very much.
Exactly. And you have a fundamental problem that if you want to get there within the space of a human lifetime, you're going to be going extremely fast.
Yes.
And the physics problem of slowing down is much harder than the physics problem of being accelerated.
Absolutely.
So Jack, do you have any point that you would like to raise?
I mean, I just thought that reminded me of the blind people describing different parts of the elephant. And we were all saying that the one-word answer would be no, and that we have to preserve our planet. But we were each seeing it from a very different angle. And that has to do with our specialties and our interests. And you assembled a very diverse panel for this.
Deliberately.
So one thing that interests me about this discussion about self-replication and evolution is our ability to control this. So it's fairly common to talk about self-replicating technology, and immediately somebody quotes Jurassic Park and says, life will find a way. You can possibly control anything that replicates, which is actually totally untrue. It's totally possible to create systems that contain error correction that goes way beyond what biological error correction does. It's tricky, and it's very likely that if left to their own devices, many people will be sloppy about it. So there is an interesting challenge that we might want self-replicating technology. It's usually not as effective as dedicated technology for doing something. But if you want to scale up something, like you want to send a probe far away and then have it unfold and build a big installation or change something, or for that matter, change an ecosystem there you want to put in a life form that can replicate, then this is a very useful tool. But it's also a tool you want to control so it doesn't go out of control, as we see by introducing the wrong species. That is possible if you design things technologically right. The problem is, the smarter the system is, the harder it is to control. My colleagues at FHI are working very hard on what happens when you get real intelligence. Actually controlling intelligent systems is very, very hard. But many of these technologies wouldn't be copied. But posthumans obviously would be probably on par or even above the AIs. So that leads to a very interesting question that the panel in general might be interested. And that is, of course, creating the right kind of control mechanisms so systems don't go haywire too much. We have it in human societies in the form of norms, social rules, narratives, reputations, police forces, etc. We have it in the terms of immune system. We have it in some sense in ecology in form of meta populations, where if one part of the population crashes, other places can recolonize it. And I wonder if we can start thinking about what kind of control system could we make to make space work better.
One question is, are you producing an artificial life form? Because when defining life, it's extremely difficult. There are all sorts of examples where it complicated things, but the definitions that I've seen have come down to the need to include something like Darwinian evolution in life. And if by that sense you are making these machines alive, that gives much less control because you're letting natural selection do that.
Yeah, and in some situations, you might want to have evolving machinery. It sounds like a great idea for adaptability, except that now you have to give up your ability to predict what it's going to do. Under other circumstances, maybe you just want robots that can go to an asteroid, scoop up the regolith, make more robots and solar panels and build a part of your Dyson sphere. So they have different uses. Sometimes you want life. Sometimes you definitely don't want life. And controlling this is a bit like people in biotechnology who want to have a good biosafety system. There are some microbes you don't want to leave the lab, and you might want to even build in ways of keeping them bound to the lab. But one of the problems might be, of course, in the future, we might be stopping. Some people might be bad engineers and forget to put in the safeguards. And then we might want to have a way of mopping up robots that are replicating out of control, because that would mess up the ecosystems and resources in space. And we might have a moral and practical duty to figure out good ways to handle that.
So, I mean, I think that's a really interesting challenge. For me, I suppose, as a biologist, I then think that the moment you've got any system that can somehow repeat itself, to use neutral language, it's got some kind of internal electronic, however, instruction manual for that. And however hard you try to be zero error in that, there will be some error. And it's worth contemplating that, given that this may happen really rather fast, it's worth contemplating that mutation rates in living organisms are themselves evolved. So it's like there's almost an optimal error rate, because that enables the organism to explore a variety of very slightly different fluids. And I would expect that the error rate would also evolve in a purely non-organic system.
I can make it brittle enough that it would never have a viable mutation over the history of the universe. I actually worked out the math with, but it might be that that's cumbersome. Let's do a slightly softer thing and hope for the best. So just because I can make the mutation rate low enough doesn't mean people will make it low enough. And then what?
So you might have recognized a bit of a subtlety in our question. So we didn't ask, is there planet B? We asked, is it time for planet B? To also think about time dimension, considering that the answer might differ with what time scale we're looking at. Now let's concretely look at a very near future. So you've been discussing on how you see progressing things. What if Elon Musk creates facts that already push things into a different direction? How should we go about that? So he goes to Mars, he sets up things there,
Well,
and it's just happening.
Elon Musk can do what Elon Musk wants to do, and he can even convince other people to pay him to do the same thing, but that's not quite the same as human civilization is spending in space. And assuming that you're not asking whether Elon Musk can change the laws of physics, I'm not sure that that's going to change our answers, because Mr. Musk has already suggested that he would like to colonize Mars, and I think that informed our answers and wouldn't necessarily change our response about whether right now is the time to do this. If he does everything that he says he wants to do, if his business case is successful, which is still a question, but if he waves his magic wand and gets 1 million people, I think he said he wants 1 million people to Mars, I don't think that answers the question of whether we are capable of settling Mars. I think we'll have to wait to see whether the next generation exists on Mars, whether we can build a self-sustaining civilization on Mars. And I think that's all very much up in the air, even within Elon Musk's business plans. So it doesn't change my answer.
So are Elon Musk plans any realistic, or do you think it's a vision that can't be realized?
I think you can send humans pretty far out into the universe. The question is whether they're going to thrive there is very much sure.
Generally,
Martin, do you want to come in on that? Yes, Martin.
Yes. I think the question is how many ordinary people would want to go to Mars. I don't think many would. It's less comfortable now than the Antarctic or anywhere like that. But I do think that there will be some crazy adventurers who will be happy to go to Mars with a one-way trip. And I think they're going to be important because they're going to use all the technology of not just computers, but of genetics to redesign themselves. And I don't think Darwinian selection is relevant at all. This would be planned intelligent design, but they would be able to, within a few hundred years, turn themselves into a new species adapted to the Martian environment. And so post-humans will be the progeny of these crazy pioneers on Mars. And this is far faster than any Darwinian selection. And I think in the same way that even if they become electronic and download themselves into that, then those machines will themselves advance not by Darwinian selection, but by progressive advances in intelligent design. So I think we've got to say it's not Darwin, it's selection of ever more intelligent and ever better fitted to the environment entities.
Martin, just following on from Martin, just take a test. Just ask a question: how many people are prepared to go to Mars? Just ask the audience.
Oh, you already asked the question, how many people in the audience would be prepared to go to Mars? You just asked. So I'm asking the same question.
Speak up. Anybody wants to go to Mars?
Depends how long it takes and if it's a business class.
There's Elias over there. Anybody else want to join in there?
Yes. Martin. Yes. Yes. Martin, can I give you a small anecdote on this? A few months ago, I addressed a terrifying audience, 1,000 15-year-olds who'd been bussed into a day of science. And to lighten the atmosphere, I started off by saying, how many would like to go to Mars? About half the hands went up. How many would go the one-way trip? A few hands went up. How many would like to send someone else on the one-way trip? All the hands went up. but then at the end, one of the kids came up to me and said, if I was on Mars, would I be able to communicate with the Earth? And I said, yes, you would, but it might take up to half an hour to get an answer. And he thought it was terrible to have to wait half an hour to get an answer. Tell that to Captain Scott.
Okay, so I would not send somebody else to Mars. Because if we want to have another habitable planet, another planet where people can live semi-independently as one could maybe on a mountain or a not ideal environment on Earth, but one could get out of the airlock.
Yes.
It's much harder to terraform Mars in that sense.
Yes.
If you have people living there.
Yes.
And then Venus is a harder, much more difficult planet to terraform than Mars. So that's why I propose that if we had to go somewhere to save civilization, whatever, because something came up that would be destroying civilization, whether it would be natural or done by people. The moon would be a better spot, or asteroids or something like that, because you could bring in things to Mars. What you need is a significantly larger atmosphere. And yeah, Mars is a smaller planet. It might not retain the atmosphere on billion-year timescales. That's not what you're concerned with. So by bringing in things, what you're talking about is things from the more distant parts of the solar system, having them be perturbed by the planets and just make slight course corrections, like we experimented with the DART spacecraft a few months ago. It would be a little more complicated, but it would be possible. And bring in lots of water, but those things would make conditions very difficult for life that's there for short times.
Yep. No, I think that's an important point. But I think focusing on timescales again, I think the humans who go to Mars, if it's a few crazy people living in capsules, then within a few hundred years, their progeny will be a quite different species. And if it becomes electronic, then of course they won't need an atmosphere. They may prefer zero G, and so they can go on into the blue yonder. And so intelligence may survive, but not in anything like we understand. And the important point is that these changes are far faster than Darwinian selection, and they would be perhaps the way in which our progeny of a very different kind could survive and could indeed go all through the galaxy.
We have a bit of a queue here, Chris, and then Anders.
Right, so I'm going to talk about a time scale of to 100, maybe 200 years, and I'm going to use Martin example of Antarctica, which I think is quite an interesting comparison here from its discovery. That first of all, a few adventurers go. They don't stay for long, it has to be said. Then what happens is that political players, as in countries, setting up bases under in the name of science to have effectively a claim of space, in that case in Antarctica, in this case in real space if you like, and but it might be companies this time rather than nations doing that, getting a foothold. Then what's happened to Antarctica is that the escalation has been in tourism. And I don't know how fast everybody else on the panel knows much better, but how fast people would be able to get to Mars and back in 100 years' time, let's say. But if you had things that were like effectively as luxurious as cruise liners going back and forth, and it was going to be a long trip, then I can imagine that going there, spending a bit of time, you're still in space form, you're not really doing terraforming it, you're building practices and things people could be in, you can go out on the dunes in it. I could imagine that being a future that isn't all about machines that are disappearing off into the landscape and doing their own thing.
Yeah. So one interesting thing about that is, of course, that building that kind of cruise ship is partially a pure technology question, partially a business question, and in between you have the soft human questions. And generally, I tend to admire Musk when it comes to the hard engineering stuff, rocket engines and steel and stuff like that. He usually knows what he's doing about. I never heard him talk about life support systems, and that makes me a bit worried about going to Mars, because you need a life support system that works well enough for at least a few years there. But the fun part is, of course, that where Musk is actually upending stuff much more radically is by making space launches much cheaper. There is a ridiculous number of satellites being launched every year now. The number of satellite launches has gone up tremendously. Astronomers are not terribly happy about the mega constellations because they are spamming the telescopes all the time. On the other hand, the Ukrainians were very happy about getting satellite communications that were hard for the Russians to get. And indeed, many countries are getting very nervous, but wait a minute, they're showing up communication networks that we don't have control over. And Musk's response was, yeah, they can shake their fist at the sky. Now, in practice, of course, if Musk annoys such a big government, he's going to get sued, and there are the normal courts of law and the normal pressures of business. But what is actually happening now is, of course, this interesting change of how the old treaties are working. Once upon a time, we had space treaties based on the assumption that only superpowers can go to space, and maybe other nation states want to have a say through the United Nations. Now, new space is kind of upending that, and nobody really knows how it will work. We can discuss how it should work or how it ought to work and try to push it in that direction. But it's very clear that there's going to be a big reorganization here. So exactly what you're going to be allowed to do on Mars or not is going to be dependent partially on treaties and the business deals that are going to be made in the next few years. So this is both an opportunity to influence things, but also rather dreadfully, we need to get it right because it's going to set the agenda for the next few decades.
So our life support system on planet Earth is extremely elaborate. So we have a well-balanced, extremely complex ecosystem. And there are lots of things that we really need. There are a lot of things in our ecosystem that critically depend on each other. So is there any simple shortcut to build this somewhere else in space, or how can we exploit that?
Build an ecosystem as complex as Earth, or something that could keep humans alive and so on?
Because those are two different.
Yeah, totally different things.
Well, something that is sufficient to keep humans alive without depending on imports from planet Earth.
So the Earth's ecosystem is not just complex, it's also very redundant. You and I were having an excellent conversation earlier offline about how many species you actually need on Earth to keep the system stable. I'd love to bring more thoughts on that. But I think if we start from 0 species on a planet like Mars, and try to import the minimum number that would keep us alive, I think we're very likely to accidentally kill ourselves. The biologists can correct me, but I think we just cannot control that level of complexity with our human technology yet, or even really understand all of the interplays and complexity. And when we try, for example, when we import cane toads to Australia to try to keep the sugarcane beetle under control, and then there's a massive explosion of the cane beetle population that kills off a bunch of native wildlife, we tend to screw things up trying to control the ecosystem here on Earth. And there's a lot of forgiveness built into the system. But I think it's very risky to try to just say, we'll just import the lowest mass of species that we can bring with us to make a stable ecosystem. I think that's a very high risk scenario.
I would possibly argue that a smaller number of species might actually be more manageable, because the multifarious interactions that can be set up with multiple species becomes very complex. We can understand, if you like, the biology and chemistry of a few crop plants and so on, and then we can, but some of you may know, most of you may know about the Biosphere 2 experiments that went all horribly wrong because they couldn't control the atmosphere in the environment that they were making, where they tried to make a sort of enclosed system on Earth to give it a whirl, as it were. Basically, they didn't have a big enough ocean, I think was the bottom line.
The concrete was off, yes.
And so if you know a particular species, and you're prepared mechanically in some way to maintain the atmosphere, so you're not actually relying on plants and animals to do it, then that might be more doable. What I think is going to be most challenging is that the one thing will be difficult to sterilize completely would be humans. And we are each of us is a multi-species community. And I'm not sure I'm up for going to Mars if I have got to be completely sterilized of every microbial cell in my body. And in fact, I would undoubtedly die if that happened. And so there is this source of multiple microbial species that under our present systems of understanding and management, I think, would be virtually impossible to keep complete control of.
But complete control might not necessarily be necessary. It might be that you can get enough. So there have been various experiments in space programs where we have had these closed ecosystems that were not as flashy as Biosphere 2. What undid Biosphere 2, I think, was they tried to have everything. And that was an interesting idea, but it turned out to be unmanageable. But on the other hand, you have, for example, the NASA's and the Russian counterpart experiment, where you basically just have, I think, wheat and astronauts, and that's basically the ecosystem. So you basically have a bunch of microbial species, a plant and an animal. And that was dreadfully boring, but apparently could be maintained. You can probably do something more advanced if you worked a little bit on it. I think the real fun part is, of course, once you're out in space, you're still going to get mutations. Especially fungi seems to find the space environment really fun. They can handle the high levels of radiation. It also mutates them. And apparently the smell of the International Space Station is slightly moldy because you can't clean everything behind all the panels everywhere. So you are still going to be needing to be able to nudge your ecosystem. But maybe if you keep it relatively simple, that might be doable. This is one of those things where we cannot use theory to determine. We just need to try it. And that's probably why cheap space and having a lot of wild adventurers trying the cheap space and trying to stay alive is very valuable.
So we can potentially have the basics, and then maybe we have a virtual reality terraforming of the planet, and that gives us the rest of the satisfaction.
Some of the big proponents of space colonization, they point in particular to the benefit of having several different colonies out there because they can experiment. They're essentially laboratories that are isolated to each other. I mean, we're talking about experimenting with ecosystems. These writers are often talking about experimenting with political systems. And while as a scientist, I see the appeal, I'll also point out that the failure states that we would all learn from would not be pleasant for the people within the experiments, and that's something we need to keep in mind as well.
This is why we want those crazy volunteers. More power to them, Linus. We're very thankful, the rest of us.
But eventually, if you want a self-sustaining sediment, you have to reproduce, and the second generation is not necessarily consent. So ethics still matters, even if we have crazy volunteers.
Just to say, thinking back to the moon, which is more feasible, then one is going to have these different companies setting up little bases, etc. But I think even though we all accept that you could do useful scientific things on the moon, the telescopes on the far side and all that stuff, what's not at all clear is how many people need to be involved, because robots are getting better at assembling complex structures. And as Anders says, one can launch a lot of heavy stuff quite cheaply now with the latest SpaceX launcher. And so it's not at all clear how many people will actually want to go, even if quite a lot elaborate constructions and mining operations and all that are being conducted on the moon.
Yeah.
I think that if we're going to do experimenting like this, probably the best place to do it would be on asteroids. There are a lot of them. They can be useful. The science on asteroids, finding out more about them, can be really for resources, because you can't bring resources from Mars very easily to Earth. Or you can bring it up to space more easily than from Earth, but it's much harder than from asteroids. And you could really do experiments without harming the central planet by these asteroids, which are very, very numerous. That's the big advantage. And they're small, so you can take things from them, put them into free space, and bring them to high Earth orbit less expensively than bring them from Earth to high Earth orbit.
So one of the standard phrases that you find in scientific publications is more research is needed. So now think about the issue of a human future in space again. What is it that we actually know? Where the things are, where you think that more research is needed?
Well, we know that humans can survive in space in low gravity. We can walk around on the moon without sinking down into the lunar dust. These are things that we had to actually test. And I think we've learned a lot about the technology of life support in those specific contexts. I think we don't know the answer to those questions about human physiology beyond a certain time scale. And for, in this case, the time scale is, what's the record for this space station? Like a year or two. So we don't know about the physiological effects of the space environment over the course of a human lifetime. As an adult, we don't know about the psychology of that kind of isolation from Earth and the rest of humanity. And as I keep mentioning, we do not know at all about the physiology of how to reproduce in space. And even more complexly, we're not even sure how to ethically test that, because most bioethicists and medical researchers are very much against the idea of experimenting on pregnant people and fetuses, and there's no way to find out whether we can reproduce in space without having to do that at some point. And there's no way to have a self-sustainable population of humans in space without being able to reproduce, unless we can download our brains into computers, which I am skeptical about, because I think we've demonstrated more ability to inadvertently terraform, or at least alter a planet's atmosphere, than we have demonstrated the ability to put a person with technological bodies. So I think we're still stuck. The big question for me, as someone who doesn't do medical research, is the question of reproduction space.
I completely agree. I also think that is kind of the big question mark where we actually don't know the really relevant stuff. There are other issues that need to be demonstrated. We need to demonstrate that we can actually do mining in space, that we can actually do manufacturing in space, and that we can do good general recycling in space. But I don't think anybody thinks that this is going to be forbidden by fundamental physics. It would be exceedingly weird if that was the case. It might turn out that it's amazingly tricky. I was talking to a space mining company representative, and we got into the issue of gravel in microgravity. In a mine on Earth, if you drill in a rock space, you get pieces of rock falling off, and then they fall down to the floor where you can scoop them up. This is super convenient. In microgravity, no, we're floating off in various random directions. You need a completely different way of dealing with this, which doesn't sound alien to an engineer. An engineer can totally find you a good solution, but which is the best solution? And which one doesn't get stopped because there is certain force of gravity that gets stuck in the wheelhouse of some robot, etc. You need to do a lot of empirical testing and testing it out. We cannot just sit down with a nice computer design program on Earth and test it out. We actually need to test it. But that's not ethically problematic like human reproduction. I think that's going to be the final step. Once we demonstrate all the other stuff, at that point, there are going to be enough crazy volunteers, and sooner or later, some of them are going to, ethically or not, demonstrate whether this is going to be possible. But it's going to take a fairly long time.
On the other end of the spectrum from human production, you made me think of this from asteroid mining. I think one big unanswered question we have is what the economic case is for it. There's certainly a lot of theories that make people quite confident enough to invest money, that there is a business case for space, but I don't think that we've demonstrated in practice that that's the case. Even the big successes that people point to, like SpaceX, are still heavily subsidized by the government. And so I think in the capitalist framework in which we're all working right now, we need an economic case to do this at all, or none of the rest of it will matter, because we won't get that far.
The big problem with this is it's economies of scale, because getting it going is exceedingly expensive. So, and the first use is clearly material that you want to have in space, not making material to bring, or mining material to bring to Earth. Because even with the reductions in costs, if SpaceX Starship and New Glenn or whatever from Blue Origin or whatever things like that live up to what their advertised potential is, it's still very expensive to bring things from Earth to space. And from a fundamental physics point of view, it's a lot less expensive to bring them in huge quantities from asteroids that are the size of football stadiums or something like that, and that have orbits very similar to that of Earth.
Martin, would you like to comment on that as well?
No, I completely agree with that, and I must say I'm skeptical about mining the moon, and especially about Harrison Schmidt's helium-3, where you've got to do strip mining in a big way, and of course it's even harder to make a fusion reactor using helium-3 than the way they're trying to do it now. So I'm very skeptical about that, but I am enthusiastic about the scientific role of the moon, especially the far side of the moon, for low-frequency radio astronomy and optical, and maybe the kind of interferometry which I asked about earlier, in the optical, that might enable you to get a resolved image of exoplanets. Maybe the question is whether it's better to do that on the far side of the moon or in free space. And but in either case, it's mainly a robotic task to assemble it.
Okay, so as the only, but I'm not usually accused of having my feet on the ground, but I do tend to have my feet and thinking on Earth more than on extraterrestrial bodies. And I'm very pleased that the next conference in this series has got the word madness in the title, because the idea that we're going to send little sort of have a new Australian exporting convicts to or even volunteers to asteroid belt experimental capsule seems completely and utterly ridiculous to me for substantial period of time. So I would have thought there was much more scope for, we're not going to terraform Mars in any time soon to the point that we can all wander around on it and breathe breathable atmosphere. We're nowhere near this. But anything that's going to be on an extraterrestrial body is going to have to be in some kind of capsule. And I might be stupid, well, I am stupid in many, many ways, but I would have thought that we could develop much more of this on the Earth if we wanted to, as capsules, so that we actually understand much more about what are the consequences of having different numbers of species in these things, different number of control systems, actually having people in there or not, or robots in or not. And that seems to me that that's much more doable than some of these other slightly more far-flung options.
I completely agree, and I think it's kind of indicative that there are not more experiments done like this. Why is Biosphere 2 just standing there? We're still actually doing some experiments, but why aren't we seeing a lot more? The fact that NASA is not actually having a very big program trying to build this kind of ecosystem is kind of telling us that they're not seriously actually thinking about it. Maybe they are just not doing it because we're not getting funding from Congress to do it. But I think we scientists in a lot of different disciplines should anyway want to build these capsules. In my own work, when thinking about the very far future, I was interested in the question, how self-sustaining could I make the hydroponic pod with solar panels? Could I put it on parking lot and have it be materially closed for millions of years if you handle it right? Do we know whether that is possible or not? You can put some interesting constraints here on sustainability, etc. That's a very relevant question. Obviously, actual hydroponic systems are commercial potential, but they're usually not closed. We have interesting things like underground farming, which actually makes economic sense in a lot of places. Sometimes for mushroom farming, sometimes for veggies in London, where actually transporting it from outside is so expensive compared to getting them totally fresh from a disused subway line with grow lights, inherited, of course, from the cannabis growers who developed a lot of indoors farming techniques that we're now, the rest of us are benefiting quite greatly from. These things are valuable and ought to be much more researched, including that thing about the stability of the ecosystem. How do I make an ecosystem that is stable? Is it sometimes that I want a fragile but very effective ecosystem, and occasionally I need to kind of fumigate the container because now it got infected with something? Or is it that actually there is a suitable level of infections and fungi that is used? These things seem to be super important research that would be super valuable both for Elon Musk and for a lot of parts of the world where we both might in the rich world and in the developing world want to use these techniques.
Okay, with that, I would like to draw the first part of our panel debate to a close. We should reconvene at 15:25 for the second part. So the second part will be devoted to questions from our attendees, either here in the room or online. Those online should just type into the question and answer function of Zoom, which for this purpose is a bit mislabeled because we really don't want to do questions and answers. We really want to discuss things. So if you have any comments, if you have some other ideas, feel free to type it in. It does not have to be a question. So with that, I should see you shortly down.
Thank you.
Into the final part of our event. And we're now eager to hear some voices from our attendees. And I guess that Elias has some of them already there.
Yeah, okay, there are already some questions. There are some comments as well, but I will go to the questions directly. For example, one of the first questions that are waiting an answer is from Peter Rosenberg. Why can't leave Mars for what it is? It's a dead, it's a comment as well, in a way. It's a dead, toxic planet. Leave the research to the rover robots. We are good at that, and move on. Is there comments from your side on this?
I think this is actually an interesting issue, because what is the ethics of changing planetary environment? And there is quite a lot of ethics that's based on human interests, that if this is good for people, if it would be good for people to go to Mars, or even maybe good for post-humans to go to Mars, then they should be doing. Others would say, actually, ethics might also deal with things like ecosystems. You can have an ecocentric ethics that doesn't care about humans, but care about the entire ecosystem. And usually people mix them and say that we should be nice to humans and other. But there are a few people who actually say even abiotic systems like Mars might have an intrinsic value, and we shouldn't be messing it up because it is what it is. The problem is defending these different ethical systems. It's usually fairly easy to convince people that people matter. It's possible to convince people that the animals and the ecosystems matter. It's slightly tricky to actually make a sensible case that entirely non-living systems matter in themselves, because you do get a lot of really crazy consequences. But it might very well be that we do declare a large part of the solar system as a natural park and say, yeah, these are historically natural, from a natural science perspective, good monuments. Let's keep them that way.
So I would take a human perspective of this in valuing and say that, yes, I think there is a real trade-off here, because it's exciting and interesting, and we may learn lots of things by humans attempting to go in small numbers to Mars, and particularly to send machines and so on. But we've also got the counter thing of, is it also actually more interesting to humanity over the course of the next century to leave it completely unadulterated, because we will become better and better remotely and in a non-damaging way to understand what is going on. And so I think it would be a pity to mess it up before we have learned as much as we could about the system.
Yeah, yes, I agree with that. And one of the things we don't know is whether it is indeed completely abiotic. Because although the surface conditions are not suitable for life as we know it, subsurface conditions in some places probably are. And there could very well be microbes that may or may not be related to us in a distant manner. And I think that's one of the things we should find out before sending people there.
I would also caution against, I've met other philosophers who similarly have said it's difficult to defend this cosmocentric idea of the intrinsic value of abiotic environments. But I think that is a very Western-centric idea. And I would just mention that there are other cultures, not my own, so I won't speak too much for them, that do recognize the intrinsic value and even the personhood of abiotic or a combination of biotic and abiotic environments, such as mountains and rivers. These cultures exist on Earth today. And while I am not a member of those cultures myself, if we are going to speak on behalf of humanity, as Kathryn Denning mentioned earlier, depending on what we mean when we say we have to consider that dismissing Mars as a dead planet might not be a viewpoint shared by everyone on Earth, despite the absence of a scientific definition of life as far as.
But it would probably be, I hazard a guess, a century or so before we were absolutely 100% certain there was no life anywhere in the crust of Mars. It's going to be hard to prove it isn't there.
So would you take a question from the audience here? Do we have
I can continue.
I mean, it's just a question where we can send something.
Maybe alternate.
Oh, yes.
Yes.
I have a question. So, I don't know if you can hear me on relevant words, but given that the panel seem to have a kind of resounding no to the overarching question. I guess what I'm wondering, and what I'd like to hear your viewpoints on, is given that there's a lot of money that's put into space exploration and space research, and given that we've talked about some of the social issues that Erika mentioned and some of the kind of sustainability issues that Chris mentioned, over a shorter time scale, should we be thinking about reallocating some of the presumably billions of dollars or pounds that go towards space research to these more, what I would consider possibly more pressing issues, or is there an imperative to?
In my opinion, all of it. Obviously, because I'm not a space researcher.
And I disagree, but here's the interesting, the we there, because the amount of money spent on space, yeah, it's big money compared to our own personal budgets. It's pretty small money compared to a lot of other stupid stuff going on in the world. Think about the annual budget humanity spends on astrology compared to astronomy. It's actually a significant amount of money that also affects important decisions, probably in a stupid way. You could argue that there is a lot of things that are not optimal and that are fairly useless. Public art, we could spend that money in sub-Saharan Africa. But the problem is that we here is kind of different. The Arts Council is not actually the development agency. So I actually think a lot of the space money is well spent money. It's just that we might want a lot of other money that is not well spent to go to better places. So I think in general, I would say that, yeah, reallocate money, but try to make good cases for it. And I think space is actually a fairly reasonable thing to spend your money on.
Yes, Martin. Yes, well, I basically agree with Anders, but you've got to distinguish different kinds. A lot of the money on space is for obviously practical things like internet, weather forecasting, environmental monitoring, etc. A lot is for defense. You can debate how worthwhile that is. I do think that human space flight is something we ought to question. And my line, and if I can plug my recent book with Don Goldsmith called The End of Astronauts, our view is that as robots get better, the practical need for people in space is going to get less. And of course, they're vastly more expensive to launch safely as far as Mars and back compared to sending robots there. So our view is that it'll be very, very expensive to send humans into space if one is as risk averse as NASA has to be when public money is involved. So I think the public money should be spent on robots and practical uses in space, but we should cheer on Messrs. Musk and Bezos if they want to launch humans into space, because they'd be launching them as an adventure, and they'd be launching kind of people who are prepared to accept a high risk, even a one-way trip. NASA, I think, could never launch people on a long trip and say explicitly that the risk of coming back was 50%. And that's why I think taxpayers should not pay for human spaceflight.
I generally am not a huge fan of human spaceflight compared to robotics. I mean, you could do a lot more science, but there are things you can do with humans in space, understanding human physiology better. And this is not going to Mars. I think that it's a very bad idea to send people to Mars.
Yes, yes.
For anybody to send people to Mars,
yes,
because of what it can do to the planet. There are environments where microbes will stay. There are lots of microbes that have been sent with our exploration vehicles because they can't get sterilized fully. There's some very hardy microbes. They're tiny compared to what humans would bring.
Yeah.
And yes, I think that space in terms of adventurism and having people in space, that's fine. It's largely a private thing.
Yes.
In the sense that Martin says, but I wouldn't want them to go to Mars. I wouldn't necessarily want them to go to the moon, but I think that's more debatable. And there's certainly small asteroids that are available in numerous amounts so that they're not this unique resource, although a few of them certainly are very distinctive.
I continue with another question from Francisco Diego. How about the destruction of planet A and the reasons this has been done, which go together with wars, migrations, etc.? Do we need economic political system B for planet B?
I guess the answer is, yeah, obviously we need a better system. But one interesting thing is, why are we destroying planet A? So wars, yeah, environmentally wars tend to be bad, but they have been a bad environmental force for relatively short time. Indeed, many of the big things that we have messed up on the planet, like killing off the macrofauna, that was not done for that reason. That was done simply because people were hungry and desperately poor and didn't really understand the ecosystem. And it seems like many of the things that have been going on have been, we don't see the consequences, and we don't have a good way of recognizing that, oh, we're going to have to pay for this. We don't have a way of creating incentives to actually care for the planet. So that might be what's necessary for actually making a better system for planet A.
I think the question in particular stated, do we need a political system B for planet B? And I think I think the answer is we need a better system for planet A that we could also use on planet B. There's a lot of people who describe space as a blank slate. And I wish I could remember the Providence's particular quote, but one of the authors I read said, there seems to be this attitude, this mythology that we'll go to space and we'll just all magically become nice. That's where the idea of these space utopias come. Of course, space is only a blank slate until we get there, and we'll bring all of our baggage with us. So we can't just decide, well, we'll just have a better political system once we get there, because we're bringing our own ideas and our prejudices and our backgrounds with us. So I think working to make better systems, technological and social, here on Earth can only help us in the future in space, where things will be a lot more fragile.
In some sense, the space environment, by being very unforgiving, is forcing people actually to figure out how do we handle the externalities. If you're living in a small space station, you're going to count every gram of oxygen and water, which means that whatever the system is, you're actually going to try to make sure that people's actions, they're held accountable for what they think. So that might be a very interesting lab or figuring out something that might be useful on Earth. Here, we might not have to count every gram of water, but it might be useful to see, are there ways of internalizing externalities? That might be an experimentation that we're about. Of course, we don't necessarily have to do that on a space station in the first place, but it's much harder to do it on Earth, except maybe if we could do it as a reality show. Maybe we could do kind of an airtight Big Brother house and then study that as a experiment and entertainment.
Maybe another question in the audience.
Yes, I'll ask, as the part of one of the organizers, I think by privilege, I'll ask one question. It's to Jack. Jack, I think you talked about asteroid. Were you saying that we can actually put up a tent on asteroids? If yes, what's the gravity consideration are you taking into? How is it taken into?
Asteroids are diverse, and certainly you're going to have low gravity on asteroids. On the small ones, the ones that would be most amenable probably to mining, certainly amenable to bringing back or moving around the solar system, then you're talking about something more like microgravity. There are some of the medium-sized asteroids where you have an intermediate case where you have gravity, so some of the engineering things, I don't know what the physiology would be there. And one of the things that asteroids might do, you might people might have to have artificial gravity for people, at least at times, for appropriate development. I think that might be more easily built on an asteroid as a machine than it would be on a space station, just because you have a lot more material very inexpensively available. But I'm not sure how much I'm answering your question. You want to probe me in some direction, or?
Well, I'd like to have others' views as well, if they can give their topics worth of input. Yes?
Why would you want to send a human there? I don't understand that. The maximum elevations at which most mammals can reproduce on mountains is not terribly dissimilar, associated with declining oxygen concentration as you move up a mountain. So I would, however uncharitable it might be, send up some other mammals in some system, not a bunch of humans, and see if they can reproduce in the first instance, and whether offspring of rats or whatever would produce proper bones and so on and so forth. And I cannot imagine us sending a human to find that out, particularly of the reproductive cycle, until it has been done with some other mammal.
So settling asteroids is, of course, as I mentioned in my part of the talk, a real old classic in thinking about settling space. But Cole's original idea was you were supposed to melt the asteroid and then turn it into a bubble, a coal bubble, as it became called. These days, I think many of us have realized that actually asteroids are not big rocks. They're actually rubble piles, which actually means that mining is simultaneously much easier, and it also is much more tricky. But one interesting idea I've seen people discuss is, what if you wrap the asteroid completely in plastic? And then you might actually use biotechnology by having algae or fungi extract whatever elements of it. It might be that you actually might create microbiospheres just by wrapping up asteroids. Now that might be rather useless for the purpose of having humans settle space. It might, however, be very relevant for getting life into space. There are some people thinking that they actually have a moral imperative to spread life across the universe, in which case this might actually be just the thing you ought to be doing. There are other colleagues of mine who think, no, this is actually super mega bad. It's one of the worst ideas ever, because just spreading life willy-nilly might actually spread a lot of suffering among sentient beings too. It's not given that having an extra biosphere is making things better. I disagree with them, but only weekly I'm actually writing a paper, co-authoring a paper about this very question. But it might be that actually shrink wrapping asteroids and having life in them could be perhaps morally a relevant thing to do. If nothing else, it might be very interesting to figure out what could grow on regolith if you water it and heat it up.
Just from my experience on this panel, I'd like to propose that any group of space-minded people who are making plans for this kind of future technology should include a biologist in the room and just watch their face to try to get the sense of how reasonable the proposal is.
I try to disguise my face, but I'm very bad.
It's an honest signal.
But I mean that seriously, not just the biologist, although that was very helpful. But yeah, put an ethicist, put a sociologist, put an anthropologist in the room. Just watch their faces as you describe it and see if you get any immediate reactions that maybe you're headed down the wrong path. Not that particular proposal is down the wrong path, but it certainly got a reaction from biology.
We have Jonathan wanting to ask you a question.
Yeah, I mean, listening to a lot of absolutely fascinating talks today, and a lot of the sort of very grand ideas about what we could do or maybe consider doing in the future, compared to what we've done so far in space and in astronomy. What we've done so far certainly feels like tinkering really at the edges compared to what we've been talking about in communities, developing communities in space, terraforming and and putting other communities on other planets, long distance travel over time, long time periods, and so on. And it's been very expensive up to now. So if what we've done up to now has been tinkering and been incredibly expensive for individual countries, how are we ever going to dream of it? Going things much, an order of magnitude or further. And it strikes me that the way that this planet is, the sort of fractured world order we've got at the moment, and have done in the past. I mean, would we require Earth to be far more coordinated? All the nations have to work together to actually make some of these sort of dreams reality, because I can't see how individual competing countries could.
Yeah. So I think
it's a question,
I think it's an interesting one, because I think getting our act together ethically and doing the right thing, that might indeed require a lot more coordination than we have right now. But the practical thing of doing these projects, the question is the cost going to stay constant? Usually it is that the prototype of something is super expensive, and the second version is still expensive, and then the price comes down. So this is sometimes called Wrightian learning curve. So, and you see them in a lot of technologies. So if you build a lot of things, generally they tend to become cheaper because you can automate it, you get better at doing it. And this is the secret behind, for example, Moore's law, which is one of the most extreme cases where we're making computing extremely, extremely cheap. Now, when it comes to space, as long as we only have a few space launches, they're going to be ridiculously expensive. And even that cost improvement is going to be very slow because we don't launch with big rockets very often. This is probably one of the secrets for SpaceX doing rather well, because they're iterating rather rapidly. It's still very expensive, but the costs are coming down. So I think one should think about how much does cost come down for different things and different technologies. So we have seen an amazing improvement in cost efficient for solar power, which is why it's competitive now. It's taken a few decades, but now it's really going. Nuclear power, on the other hand, where we build very big power plants with ever increasing safety, the cost has actually been going in the opposite direction, become harder and harder to make power. So I think in the long run, space might become quite cheap. But that's the long run. And usually if it becomes cheap enough to people to iterate and tinker. But what has happened so far is, of course, everything is a gold-plated project that needs to be approved by a bureaucracy at NASA or some other major organization. And that's going to keep it impossible to do.
I'll also note that your idea that space activities have mostly been tinkering is only true beyond Earth orbit. Low Earth orbit is an extremely sturdy and heavily populated space for industry, for military uses, I mean, we have people living there on a continuous basis, which makes it sort of boring, which is why most people don't think of it as being outer space. It's very nearby, and it's just not as interesting as it was back in the days. But there are, I think, very useful lessons we should be learning right now in low Earth orbit about international cooperation, public-private partnerships, because there are a lot of ethical and social challenges happening in low Earth orbit right now to do with protecting the space environment. In this case, not protecting Mars from microbes, but protecting low Earth orbit from getting filled up with debris, which could very much seal us into our own planet if we really screw it up. And so this is a good lesson for us to learn now before we continue on with the rest of the solar system. Questions of land use actually are related to low Earth orbit when it comes to where we put our launching facilities, which tend to be in places that do not have a lot of local political power. And so I think that's important for us to not forget about that part of space where we are having a lot of non-tinkering activity. It's not as exciting as the idea of colonizing Mars, but I think we can learn a lot if we pay attention.
Yeah.
Martin?
Yeah. Yes. Well, I mean, I think it will develop, and think of civil aviation, which was very risky and expensive in the 1920s, but has become routine, done by the private sector. And I think that same development will probably happen in the future. Of course, the development of space has been distorted by two things. First, it developed first to make ICBMs for nuclear bombs, and also for national prestige purposes, the Apollo project, and they were both hugely expensive. But if we imagine that the development is motivated by ordinary civilian economic needs and priorities, then I can imagine that we can get ever more advanced projects, just as we do in aviation and in power generation, and as mentioned. But of course, it has been distorted in its development by the huge acceleration caused by the needs for defense in the 50s and 60s and the Apollo program.
I think the Apollo program was funded so well because it was considered very closely related to the defense program.
Yeah, that's right. To beat the Russians. Yeah.
Yeah, because it was, you were spending money that made the country more secure in some sense.
Yes. Yes. And if that momentum had been maintained after 1970, there would have been footprints on Mars long before today, but there was no motive, obviously, to do it.
Right. Yes, it was just, it would have been so, the amount of money being spent on NASA at that time as a fraction of the gross national product, it was much, much higher than today.
Yes.
More than an order of magnitude.
Yes.
Can I just say then, so what you're saying is that political competition seems to have driven, or it is a driver for space exploration.
Yes, but is it now competition between tycoons who want to do one up and the other boss of some big enterprise?
Okay, I think we can go to one more question from the remote audience. Joyce is asking, what is our obsession with colonizing other planets and not preserving the one we are already in? Has the history of colonization not shown us that it breeds violent environments that make the inhabitants irrational in the way they interact with this planet? Shouldn't our efforts be in finding better ways of coexisting with the ecosystem we already inhabit?
Well, maybe if I start on that, the answer is evidently yes. And that we should indeed be trying to fix our own planet. And as everyone has said, it's not practical for us to have a mass emigration to anywhere else anyway. And so we need to deal with those issues. And there have been some comments, and although I was frivolous about how we shouldn't be spending any money on, I should be receiving all of the funds that would otherwise go into space research, which is obviously my top priority. However, I don't know what the amounts are. Maybe some of you do, but the amount of money that is spent on trying to manage the planet's surface and understand how to do it is a very, very large amount of money already. And as Martin's already referred to, much of our Earth observation now of how our environment is changing is indeed being done from space. So, so I don't really think they're alternatives, because I can't ever see that we're going to spend some terribly significant fraction of the entire planetary effort on trying to go to space. And so I think that it's exciting to do so from multiple perspectives, but not sending people particularly. But they're not alternatives.
I very much appreciate this question, because I and a lot of people I work with write a lot about this framing of colonization, space colonization. You might have noticed I try to avoid the term. I try to say space settlement instead, even though settlement has its own troublesome historical connotations, because so much of the new space industry, going all the way back to O'Neill, I would say, and even before that, is framed around the narrative of colonization. Specifically colonization of North America. Americans love this model, the frontier thesis. Oh, we're out of space on Earth. The only way we can grow and not stagnate as a species is to go out and find our destiny among the stars. It makes for great rhetoric, unless you know anything about history or come from colonized cultures. And so a lot of us are trying to move away from this narrative. There's an argument that people make that, well, there, as far as we know, there's nobody on Mars or any of these other places. There's no indigenous life for us to damage, and so we can just keep colonizing. But I love the way the question was framed, because it pointed out that the mindset of colonization itself leads us to damage a lot more than indigenous life, and that includes the environment. It leads us to set up structures that are really harmful for everyone involved.
But if there is life on Mars, then sending human, even objects, is risky, let alone people, is potentially a serious issue if one's interested in understanding what was on Mars and how it might survive. In the last 500 years, a significant fraction, arguably the largest single cause of extinction of species on planet Earth, especially on oceanic islands, has been the arrival of one species into the geographic distribution of another species that could not coexist with it. And so when a whole load of mammals arrive on oceanic islands, they ate their way through the terrestrial birds, for example. Well, we're not talking about that on Mars, obviously, but there's no reason to suppose that there can't be microbial equivalents which could go in either direction. And so, so the risks of colonization in a serious way of Mars are not completely negligible, I would argue.
And so it's important to really interrogate what our motivations are, what narratives are we putting onto whatever project we're trying to propose. Actually consult with historians about whether we're repeating the mistakes in our past, and coming up with, I would argue, better framings for what we want to do or not to do in space, instead of just sticking with whatever mythology is popular in the space industry.
Martin, and in terms of
yes. I think we should avoid the rhetoric that's often used in space and other things when it talks about we, meaning the whole of humanity. There are some contexts where we do want a global consensus and we've got to have a legal framework, but the kind of things we're talking about don't require a global consensus. They require maybe a large business or maybe one nation even. And so surely we want to encourage variety. We don't want uniformity because we're not doing anything on the scale of the whole human race. And I think it's dangerous to have this idea that the whole of humanity has to move in unison towards some great goal. We should allow variety, and if a few people want to go to the moon, then fine.
Can I just say that Elon Musk has microbes in his body? One person.
Well, the things about potentially habitable environments by some types of life on Earth, this is something that is taken into account in planetary exploration. And NASA indeed has a planetary protection officer. And there are international standards for sterilization of spacecraft going to places like Mars and Europa and Titan and Enceladus, and the Cassini spacecraft that orbited Saturn and did some wonderful science for about 13 years was purposely thrown into the planet so it wouldn't hit one of these moons that has potentially habitable environments, because it was not sterilized in the manner consistent with planetary protection before launch.
I do agree with Jack that scientists have been very good about following the guidelines written by scientists. However, there's a more recent case of a private organization on a spacecraft called Bereshit Lunar Lander by Space IL, which is an Israeli company. There's a nonprofit that sent along a library of data to just sit on the moon as a sort of a representation of humanity. And the guy who ran that nonprofit decided at the last minute, as he was putting the library onto the lunar lander, that he would stick some tardigrades, sprinkle some tardigrades onto the tape that was sticking the lunar lander on it, sticking the library onto the lunar lander. Tardigrades are microscopic, extremely hardy life forms that can survive radiation, dehydration, and be dehydrated and come back to life and keep reproducing. And he did not report this to the authorities that you're supposed to give your biological inventory to when you launch spacecraft. And then the Beresheet lander did not become a lander. It crashed into the lunar surface, scattering potentially tardigrades across the surface of the moon. This was not technically a full violation of the planetary protection protocols because the moon is not considered to be a category of potential environment that we could really contaminate. But it, I think, is an excellent example of the different motivations and adherence to these sort of scientific integrity and planetary protection protocols. And I can only imagine that we're going to have more cases like this as more, frankly, non-scientists decide to send technology and humans to space.
Yeah.
Okay.
Yes.
Yeah.
Just ask if anybody else wants. Yes, there you are. Yeah.
So was a great talk. My question is to Professor Martin. You were speaking about intelligent design and that intelligent design need not be aggressive. So I was thinking, my question is if Darwinian evolution has a property of aggression, us humans being a product of that, wouldn't that property propagate to our design?
Well, I mean, I don't know really, but the point I was trying to make is that intelligent design is much, much faster than Darwinian selection. If the machines design even more intelligent machines, they may or may not decide to incorporate aggression. It's not at all clear. Things get very uncertain. And maybe if I could backtrack slightly and make a comment relevant to Cassini and all that, I think one of the most important experiments that we should do is looking for life on Enceladus or Europa, because finding any life there would indicate that the origin of life, which as we know is still a mystery, was not a rare fluke. And if it happened twice within one planetary system, it must exist in a billion places in the galaxy. Whereas now we can't rule out the origin of life being unique to the Earth. And of course, Mars will be ambivalent because it's possible for life to go from Mars to the Earth and vice versa. So we haven't talked very much about aliens and whether we will be encroaching on other species habitats by it going out into space. But the key question is life a rare fluke or is it widespread? And that's why a positive result from Enceladus or Europa would, I think, be such a fantastic discovery.
So I fully agree with you that that is the key question, not whether there's life somewhere else, but whether there's a second genesis.
Yes.
But to me, actually, the places I'd find least interesting to identify life are places like Europa and Enceladus, because I think it is possible to bring life on timescales that you have impacts and material being shoveled back and forth, carried back and forth between the planets. It's much easier between Mars and Earth.
Yeah.
But I think it's possible between Earth or Mars and Enceladus and Europa, especially going out there. And Mars, it would be much easier to either bring it back or send something there to do more detailed studies. Mm-hmm. If you found it outside the solar system, then that's the great evidence, because then yes, the only two possibilities are a second genesis or interstellar panspermia. And in either case,
Yes.
you have the universe probably teeming with life.
Yes.
Could I just say briefly that if we find life anywhere else, whether it be Mars or another moon somewhere, it will be completely and utterly obvious from the biology of those organisms whether they have a common ancestor or not. This really won't be under any question because they're highly genetically related between Mars and with the same sort of biological process. It's so vanishingly unlikely that there would be so many of the biochemical processes in common if they didn't actually have a common ancestor. So I think we would be able to tell pretty.
Well, the problem is that if you found life there, yes, if you actually looked at it under a microscope or whatever, you would be able to find that out easily. But the amount of information that would come back on decadal timescales from discoveries at Europa or Enceladus probably would be very, very minimal.
So I'd like to get back to the original question, actually, because I think I have one angle to it that's slightly different from Martin's point. When looking at artificial intelligence safety, we have a bunch of various ideas floating around, and two of them seem to bear on this question. One is the orthogonality thesis. This is the idea that you can combine any amount of intelligence with any goal. In humans, generally, people have human-like goals, and smart people are good at achieving human-like goals, and very smart people might be eccentric. But we can't really have totally arbitrary goals. That might not be true for machines. It seems to be totally possible to combine any level of intelligence with any goal, which is very disturbing, of course, because you could get very crazy goals for very capable machines. However, it might also mean that if you're designing a machine and know what you're doing, you can actually give it, for example, a very peaceful goal, and that it's going to keep to that. Against that is another big idea in this field, and that is instrumental goals. If my goal is to play chess or to terraform Mars, I need some resources. And the more resources I have, better I can build chess computers, so the more water I can add to Mars. So actually acquiring resources would be useful for both of those goals. Indeed, for most goals, having more resources, preventing others from interfering with me doing my goal, etc., are useful. So this is the scary part that you might expect very capable intelligent system to also amass power, amass self-determination, and make it very hard to turn themselves off. So you have two slightly opposed ideas here. It might very well be possible to design safe AI that behaves itself and is allowing itself to be turned off if you design it right. If you design slightly wrong, however, there might be a kind of attractor point where it's getting dangerously unruly. And there is a big debate about how the likelihood and under what conditions these things entail. So this is, of course, about the ultimate limit of secular intelligent design. Can we secularly intelligent design machines that behave themselves or not? It's probably even harder to do this reliable for the design of biology or humans, because there you already have this evolutionary background and a lot of noisiness and randomness built into the system.
Could I just make one point? Computers were invented, people used them for good and bad purposes. Genetic modification has been invented, people can use them for good and potentially bad purposes. And if we can have robotized remote things, then people can invent things that are more malevolent as well as ones that might be perfectly controlled. So people are
I have a question kind of building on that to do with the kind of concept of post-human and secular design and kind of manipulating genetics and moving past Darwinian evolution. The question I wanted to ask was, I guess it's a bit of a sort of a thesis, this ship like triggers doing sort of problem. A lot of this conference is focused on providing solutions for humanity, saving humanity. But if we're creating artificial intelligence or robot progeny essentially, how much of that is a solution for humanity and how much of that is actually just providing a legacy? Because especially for example, in genetic mutation and evolution, that's not be accessible on a global population level, that's going to be a few very adventurous individuals who are going through that. And is that really a solution for what we do the whole, or is it just kind of, I guess, making our mark on the greater universe would be my question.
I'm certainly interested in this question, and I think there have been a big philosophical debate about various forms of human enhancement. And in many cases, it's kind of about, okay, that's good for the person getting enhanced. If I take a drug that makes me more creative and I enjoy creativity, that might be good for me. It might also be good for others. We could say that's nice. There are other things that are more controversial. But if I were to undergo some transformation that turned me into an entirely new kind of being, let's say uploading my mind into a computer, some people would say, that's not good for you, Anders. That might produce a very happy computer maybe, but it's kind of not good for you. So why would you, Anders, want that computer to exist? Now, I happen to be kind of happy with that idea, actually, because I have a peculiar philosophy of mind and peculiar ideas about personal identity. Other people don't agree. And the same thing, I think, happens for humanity. We like to imagine that we have not just a legacy, but a continuous legacy. Not just a few beautiful monuments slowly crumbling into dust, but actually that our society continues and evolves to a better society that continues and does amazing things. And we might similarly want the biosphere to keep on going in the right way. Not just one morning it all turns into something completely different, even though that might still be an impressive thing. That continuity is quite important in how many people think about it. This is partially why we're very afraid of global disasters and the existential risks and the end of the biosphere. We might want to prevent it from being cut off. Now, the question is, these enhancements and modifications and possibilities, are they the right kind of transformation that are allowed or not? And this is where we have a big deal of disagreement. There are some people who believe that there is a natural order that we must not mess with because it's a moral order and we have our place in it and we should not allow it. Others would say, actually, we think this is a fluid order. We're evolving species. We are changing things around. There might be stupid and immoral things that we still shouldn't do, but there is a lot of allowed ways of changing. And then there are other people who say, no, anything goes, actually. Nothing is true. Everything is permitted. But we probably don't want to run our society like that. That's a total mess. So the interesting thing here is, of course, finding compromises about that. If I want to take my cognitive enhancer pill every morning, some people say, you're cheating, Anders, at being an academic. You're getting an extra boost over us who are merely drinking tea for morning coffee. Others will say, well, I have read Anders' paper. No, it's not helping much. And we might similarly want to think about what forms of continuity and transformation do we allow. And I think that we here is going to be quite interesting because it's going to be very different groups that have very different views. Different cultures already have very different opinions about what forms of genetic modification should be regarded as allowed with humans or the environment, for example.
Okay. So from the audience, because there are two questions that I can distinguish here. There is a kind of conversation actually between the audience. One question is from Amy Rees. Government agencies may have stated missions and structures/networks in place to support downstreaming of intentions, etc., to the societies that they serve, with potentially profit-driven private ventures rapidly developing, and in the absence of relevant legislative/treaty obligations, how will the commercial interests of evolving groups in space exploration impact on the efficiency of wider sharing of useful new innovations to tackling climate and ecological pressures on Earth, planet A? And she continues, particularly where there might be greatest need, but not greatest wealth, will chasing of a planet B vision leave planet A behind?
That was a complex question, but I just want to pick out one thing. In the absence of an actual space lawyer, I'll speak for the space lawyers and point out that private entities are not covered by international treaties about space. The The main one, the Outer Space Treaty of 1967, was much more focused on national powers. I think we were discussing this before, Anders, because it was written in 1967 during the height of the Cold War, and was mostly focused on things like saying, let's not put nuclear weapons in space, no national appropriation of territory in space. But it didn't, so it left out quite a lot of detail, didn't close many loopholes about private entities because they weren't worried about that at that point. But it did say that private individuals and corporations and such are subject to the continuing approval and continuing supervision of the nation states that launch them. So much of that, the space lawyers tell me, is so far untested in court, but that doesn't mean that it won't come up. It surely will. And the treaties do apply in some sense to private entities. It's not that they just have a blank check here to run off and do what they like without any legal supervision. Just wanted to correct that.
And if they did, they would probably have a big problem that many of them are quite dependent on the goodwill of their local government. Musk can be annoying, but he is not annoying the American government too much, because then the bureaucrats will, as he discovered to his horror, make things complicated. Right? But I think there is something interesting that also we were discussing in the coffee break here, and that's the democratization of space, which sounds very nice, but as you pointed out, that kind of means that it's not just big nations and companies, but smaller companies that can get into space. There is a real question: what could we do to really democratize space, and would we actually want that? The tardigrade example might show that, yeah, if we do that, a lot of people are going to do some things that others would say are really, really bad. So it might also be that you might want to democratize, in some sense, the control or influence over space activities, which is much more tricky because governments absolutely hate it when the public interferes with what they're doing. And that would actually be one of the consequences if you actually honestly democratize the influence of space.
I can imagine them sending the subpoena to Mars to demand Elon Musk come back.
Well, this is an interesting question that I've asked space lawyers. So many of the human rights issues that have to do with legal processes in space is how would you, even if you had laws in place to protect, for example, the rights of workers on Mars, how would you notice the problems? How would you enforce the problems? And while observation and noticing the problems is one issue, enforcement isn't actually that difficult at the moment, while most of these companies, including Elon Musk's, have most of their assets and perhaps their leaders back here on Earth. So if SpaceX went off into space and broke a bunch of US laws, for example, their assets would just be frozen on Earth. It's actually not that difficult at the moment, the way we have it set up to enforce these laws.
And there is even a kind of economic gravity. Right now, Earth is where all the money is. The Martian stock market is not very interesting for the moment. At most, it would be a few robots sharing messages over radio. And if Musk moves to Mars, he's going to be far away from most of the stock market. In fact, he was probably going to want to put most of his economists close to where the market is, which might mean that actually going far away from Earth is bad for business. If you're running your big corporation, you want to be there. It's a bit like the Roman Empire. All this, the leading Romans wanted to be in Rome because that's where the politics happens. That's where the money is. And this might actually be making it rather hard to move far away from Earth because you're going to be out of business. The news you're getting is going to be old. You're not going to get the latest computer games and streams and useful way. There might actually be a kind of extra cultural gravity of Earth that might be tricky to overcome.
Martin?
Yes, no, I mean, I agree with that, but going back a point, I mean, I think the regulation that we're going to need when there are some small actors in space, it's no different in principle from the way international aviation is regulated, or the way we would like to think that the internet would be regulated internationally. So I think it should be possible to have regulation which encompasses both nations and private, as happens in aviation. So it's not impossible, I don't think.
And I'll point out there are other analogs too, Antarctica and the law of the sea.
Right, yes.
Okay, thank you. Stefan, you want to?
Yeah, my question is quite simple. Spacefaring, Is that human madness? Are we inflicted by some meme? I have no idea whatsoever. Is it?
How do you find madness?
Yeah. Insanity, I guess, you know, in a sort of simplest way of saying it. I know we had this discussion, Martin, I, and Ilya. It's very difficult to pin down. I only wish Mukash, other committee polymath, our other committee member, he developed that question and thinks that we are on the right track in relation to madness. So it's a good question. I suppose it's kind of a mental illness, I guess.
Well,
insanity, mental illness.
I'm not sure how I'm interpreting your question, whether it's unattainable, a goal that's unattainable because we're delusional in that sense. That remains to be seen. Although we have made progress in space so far, it's not completely unattainable. Whether it's an illness in the sense that it's damaging us, I think also remains to be seen. But I don't see strong evidence of that so far. I think that any damage that comes from our activities in space is self-inflicted by other systems that are infecting our society, not a fault of space itself.
So I think one way of defining madness is saying that there is something inflexible, something delusional about it. The most mental states that we will say, okay, this is something we should take you to a psychiatrist for, involves that an element that you cannot live your life as you want. You can't function in society. So there's both an element of irrationality. You can't function in the world that exists. And there is also a bit of value here. You're not getting the value you're hoping, and you or others are hoping out of life. Now, space is interesting because certainly there is a fair bit of human irrationality. I love the point about how we've been thinking about these other worlds and quite often conflating somewhat religious ideas. We're projecting various narratives about the frontier, etc. But dreams are irrational, but they are quite often good or educational. Some dreams can lead you to do bad things. The really interesting part, I think, is what are the forces that make us rational about it? So the Wright brothers wanted to fly, which was a stupid idea. A lot of people have failed before, but they have taken what had been learned about heavy of an air flight and put it together. And maybe they were even motivated. I don't think it's the case here, but maybe they want to fly like angels. That didn't stop them from building a functioning airplane that then had various effects in the world. So just because irrationality or even madness doesn't stop us from having consequences. I think this is your point exactly. So I think the overall question is not so much, is it mad as, is it bad? And I don't think it's bad. I think we might want to spend our money wisely, and it's not the most cost-effective way of saving Earth. But it's still, we're learning a lot of valuable things that are worth doing. And there are other things that are way less cost-effective that we probably should be doing less of. And I do think we learned something very curious about ourselves and our mild obsession with space. Just like humanity has been spending enormous amount of effort on astronomy, even though the practical utility of that was relatively limited, even when we believed that astrology would tell us the future.
Okay, thank you. There's another question from the audience here. I have one question here still. An anonymous attendee writes the following. Dear panelists, the conference title poses a question. Is it time for Planet B? Much of the discussion has revolved around issues related to the case where the answer is yes. Regarding the opposite viewpoint that no, it is not time for Planet B, what kinds of sound actions do you think could realistically be taken to help the future of humanity and life in the Earth-bound scenario?
That's your talk, I guess.
Well, from an environmental point of view, yes, the pressures that we put on the biological system, I think, need to be addressed. And when I look at all of the measures by the world's environmental agencies and conservation groups, internationally and intergovernmentally, I fear my conclusion is that they're very often not tackling the underpinning causes of the challenge, which I tried to address in the talk today. I think we've also got, of course, speaking about something I know nothing about, but I think we have got the challenge of the governance of the planet increasingly facing us, the tension between governments, companies, etc. And one of the great fears that come up when I talk about starting to culture our food in a more industrial type manner is that are we handing the power of our consumption into the hands of a few big powerful companies? I would argue that this doesn't have to be the case, because if it's run by renewable energy, in principle, it is more distributed than the existing sources of power. But I do think that, and I think that this is an issue which is really orthogonal to this food production exchange system. We've got to deal with that tension.
Although even your proposed solution wouldn't save us in the long run, right? Because if you get us back down to 6.5% land use, that's only 3 doubling times to get us back up to above the
yes, well, that's another issue which is probably beyond today, that what happens to the human population once it stabilizes, let's say late this century, I think is an immense human challenge. And you're already seeing governments who are seeing an aging population putting in incentives for increased reproduction. And to my mind, we should be looking for managed reduction population. And essentially the world system has not worked out how that blank it is going to do that.
Well, partially it's also because demographers admit that, yeah, we understand aging and mortality pretty well, but fertility, that can go in all sorts of directions for all sorts of reasons. So that is the tricky part of making any kind of population predictions, because it is literally dependent on some cultural aspects.
So Martin.
Yes, well, I agree with all that, and I think this century is uniquely problematic and difficult because science empowers us hugely, but it presents us also with worse risks than we ever had. And we just have to do the best we can to control them. And politics is getting more difficult because of social media and all that. So I think there is a growing problem. But the one thing that we can be absolutely sure about is that going to a planet B is a dangerous delusion. We've got to solve these problems here on Earth, and we could do with optimal deployment of the technology we already have, let alone the technology we may have by the end of the century. But of course, the downside is that this technology is so powerful that even a few bad actors can really scupper all the benefits. So that's why this century is especially crucial.
So we're discussing space exploration. We've been discussing the need to care for our home. Do you see these things in conflict? Or do you see where these things could align? And I would like to take a round starting with Erika.
No, I don't see them in conflict, with the exception of the funding battles that Chris and I are apparently going to have. No, because so much of just this conversation today has gone from space to Earth and back again. We can easily use our what I was talking about, the psychological flexibility, as I mentioned in my first statement, that we have when we talk about space. And if we can learn to bridge the gap that Andrew was talking about, to let that imagination be bridged towards next Tuesday and the choices we're making today, I think that that benefits both areas of the conversation, both Earth and space. And aside from conversational tactics, we use space today to do Earth science. It's very, very useful for Earth science. And I think just simply in that sense, space and space technologies has been extremely helpful for helping us understand our planet, what we're doing to it, and how we can do better.
Yes.
I agree with entirely with what Erika is saying, but I do think that there is one risk. And I think of it partly in you remember the discussion of climate change, and are we going to put lots of stuff into space, sulfur, reflective shields, whatever. is that thinking that we really could do this in a big way could delude people into thinking that there is some silver bullet out there in space that's going to help solve our problem. Therefore, we don't actually need to deal with them quite so urgently on Earth. So I think it is the risk of distraction, if you like, rather than an actual risk in the sort of research and development community.
But I think that risk of distraction also happens because it is far away. If the government tomorrow said, here is our plan for putting sulfur aerosol into the stratosphere over Yorkshire, people would react rather strongly. Suddenly, it's a practical thing. There is going to be costing. There's going to be discussions about, well, how does this impact the NHS, and so on and so on and so on. Once you get to a practical issue, suddenly it handles very differently. And I think one of the big problems is, as long as you hand wave towards geoengineering to fix something, or a hand wave towards space as a way out, you don't have to take it seriously. If there was actually a discussion, okay, the government is planning to figure out the ticket price for going to Mars, it would actually change how we think about it. Now, that is not the more realistic cases here. I do think that the problem we have is that a lot of people today have given up a bit on the big hopes and thinking that, no, we can never do anything except that maybe change the tax rate a little bit and change a bit of institution, rather than actually we could build a global machine that sends information everywhere. That's the internet. That's a machine that's surrounding the Earth and totally transforming culture for good and ill. That's something we did. We have a football pitch-sized machine orbiting above us right now, faster than a rifle bullet to do space size. We are literally creating matter out of energy over in Switzerland with particle accelerator. These are outrageous things that actually do exist. These ones, except for the internet, are not everyday phenomena. I think the problem is that for a long while, space has been far away. And I do think that, it's kind of ironic, because when I'm getting on the train tonight to get home to Oxford, I'm going to travel much more further than it would be if I could travel vertically to get into space. I'm going to, if that train was vertical, I would be above the International Space Station, I think, which is kind of disturbing in many ways. But the legacy of much of the Apollo program was that blue marble picture, showing Earth in a context. Actually had a pretty big effect on the environmental. Maybe one shouldn't overstate an iconic picture, but I think it makes things real. A lot of people who's been up in space talk about the overview effect when they actually see Earth for real and they realize the situation of fragility. And that is a transformative personal experience. So I do think space actually is quite useful for looking back at Earth and changing how we think about it. But we need a good way of getting that overview effect into everybody's life.
Okay, Martin.
Yes. Well, just brief comments. I mean, I certainly think that exploration of space, just like exploration of the ocean depths, is something which should be part of our general endeavors, scientific, environmental, and obviously we get valuable spin-off. But I also think that the search for a SETI signal is something which, though I wouldn't bet very much on it, is worthwhile, and understanding life, finding evidence of vegetation on another planet, even if we don't find a SETI signal, will be very important in changing our perspective. And I think everyone's views on the world are changed compared from those in the Middle Ages because of our vaster horizons. And I think in the same way, we all want to explore, but that doesn't mean we want to prioritize searches for planet B or mass emigration.
I certainly agree. And I'll just bring back something towards that blue marble picture. And this is a personal opinion from someone who was very young at the time, so the perspective was not necessarily the same as most people, but I remember more the Earthrise from Apollo 8 as the shocking picture, and the one that really showed new perspectives on this planet at that time. Do you agree, Martin?
I agree. That's why, and that was 1968. And
Right.
That's why I think 2068 is when we want to have this lovely image of an exoplanet with some vegetation on it.
Well, I think there's certainly a reasonable chance, but I guess the spectrum would be what's telling the vegetation.
Sure.
The vegetation is there.
Yes.
In terms of a detailed picture that has the resolution of that Earthrise picture,
that's much harder.
Fundamental difficulties.
Sure. I know.
Unless the SETI folks find somebody who's going to send us that picture.
Right. Right.
So I would just wonder, obviously, some of these images have become absolutely iconic and are really important in many ways today. But I wonder whether we wouldn't simply have found other images. We show images of burnt stumps of tropical forest, for example, in many contexts. So is it that these were convenient images that we allowed to illustrate what we were thinking already, or did they actually generate a perception difference?
So I actually think Earthrise and Blue Marble do have that power. Can anybody cite a famous stump picture? There is thousands of...
No, because this one was successful.
Yes, but why? And Fred Pollack was a future studies person in the 1950s who did excellent job. So everybody has forgotten him because his idea seems so obvious these days. That is, we use certain images to think about the future. Every culture has a set of these images. It's surprisingly tricky to make an entirely new one, but you play around with the use of, when I start talking about AI safety, people immediately bring up the Terminator, regardless of whether it's a good idea. And I think the Earthrise picture and Blue Marble, they show a particular kind of image showing Earth isolated in a wider context. That doesn't tell us about the environmental emergency we have right now. You can use other pictures for that, and there is in some sense a standard set of imagery that we use whenever we want to show dreadful things happening in the Amazon jungle. But they're not necessarily iconic. I can't just throw up one of them and they're getting a whole set of meanings. I think that was powerful because it contained a whole bunch of meanings, or rather, we added a lot of meanings because it is, of course, just a picture of just a planet. Except that it means so much to us, and we have added cultural layers to it that are very deep and very complex. And there is no particular stump, no matter how important, that has gotten that in our environmental imagery.
Rectangular cut forest.
I just want to mention one more picture that might be in that set. And that was one that was taken specifically to be an iconic picture, which was the pale blue dot picture, or pale blue dot collage, where Voyager 2 looked back at the planets and Earth being a pale blue dot and how small it is in the solar system and by extension, much more in the galaxy and universe.
Okay. Thank you so much for everyone on the panel. I think it was a wonderful discussion. So this ends our panel debate.
Right. Right. Thank you very much.
Thank you.